What if the universe doesn't have an edge you can touch, but it still has an edge you can reach, just not with your hands? Stay with me, because in the next minutes, I'm going to show you how people went from drawing walls around the sky to measuring a horizon that isn't a wall at all. And there's a twist you'll want to hear. The real edge moves, even while you're looking at it. Here's the plan. We'll start with a simple question most of us ask as kids. Where does space end? Then we'll look at the first answers people tried, the ones with ceilings and shells. We'll test those ideas against what we know now. And by the end, you'll have a clean picture of what edge means today, something you can explain to anyone in 1 minute. The trouble starts with language. Edge makes you imagine a fence, a cliff, a last step before nothing. That image is strong. It works for maps and yards and rooms. It does not work for the sky. But for most of human history, nobody knew that. And honestly, why would they? If your world is farms and seas and mountains, then everything important has a border. So of course the sky must have one too. Picture a fire at night, long ago. Someone points up and asks, "What's above that?" The easiest answer is a lid, a dome, a roof laid over everything. Maybe it's made of crystal. Maybe it carries lights that move when the dome turns. It explains sunrise. It explains stars. And it fits how your senses work. You can see the ground meet the sky in a neat line all around you. That line looks like a real edge. Now imagine standing in a walled city. The wall is safety. The gate is order. When storms blow, you face the wind and think, "Good thing we built a barrier." People carry that feeling into their stories. A good world is a fenced world. Beyond the fence is chaos. So when they imagine the universe, they don't picture endless open water. They picture a strong circle, a clean border, a sky you can lean a ladder against. These early answers weren't silly. They were practical. They let people mark seasons, predict floods, set planting days. They kept time. They tied sky patterns to life patterns. And they did it with tools you could make by hand, a stick for shadows, a bowl of water for reflections, a place on a hill to watch sunrise move along the horizon. You build ideas with what you've got. But there was always a crack in the wall. Sailors notice new stars as they head south. Travelers see north stars rise and fall with latitude. Those little shifts whisper, maybe the ceiling isn't flat. And at some point someone thought, what if the sky isn't a lid? What if it's a shell and we are inside? That's a step, but it still keeps the same frame. There's a hard surface. It's just round now. The next nudge came from patience. When you watch the sky night after night, the stars keep their shapes, but they slide a tiny bit with the seasons. The sun shifts along a path. The moon climbs at angles that change. Patterns repeat, yet they also drift. A solid dome has trouble with that. Something more flexible fits better. Spheres inside spheres, gears inside gears, hidden wheels that turn with different speeds. Even that clever model hits a wall when you start to measure carefully. The planets wander in loops that don't fit perfect circles. The timing is off by small amounts that add up, so people add more wheels, more terms, more fixes. Each fix is smart on its own, but as the stack grows, so does doubt. A neat choice for a ceiling gets messy when you ask it to carry everything. Here's the first open question for you to hold. Why do we need an edge at all? Is it because the sky forces one on us? Or is it because our brains don't like no boundary stories? Keep that in mind as we press forward. Over time, better maps, longer voyages, and simple math eroded the old ceiling. The earth curved. Shadows proved it. Ships slipped below the horizon and did not fall. And a globe, once just a thought toy, started to look like a fact. But if the earth is a ball under the sky, what is the sky? If you throw out the flat roof, you can throw out the solid shell too. New tools made new tests. Simple lenses made faint things bright. Faint things turned out not to be little holes in a screen. They were suns. The lights on the inner roof story broke. With that, people began to flip the whole stage. Maybe the sky wasn't a surface we sit under. Maybe we're in it. Not inside a dome, but inside a space that has no ceiling. So where's the edge then? If there's no lid, how do you stop? Here's the second open question to keep in mind. What if the edge is not a place in space, but a limit in time? Let's get specific for a moment. Think about your phone light on a foggy night. You can only see so far. Past that, the fog blocks the beam. The edge of your sight is not a wall in front of you. It's just as far as light has made it through the mist. Now swap fog for time. Light takes time to cross distance. If something is very far, you don't see it as it is now. You see it as it was. That means the farthest thing you can ever see is set by how long light has been travelling since the first light turned on. Right here is the click most people need. The edge we talk about is the edge of what light has had time to reach us from, not a fence put up at the end of space. If the universe has been making light for a certain number of years, you cannot see beyond that number of light years. That's simple. The edge of sight is a clock. Before we go deeper, let's lay out the challenge in plain words. Our heads want a clean border because borders make us feel safe, and they make stories easier. But the real cosmos gives us a horizon that moves as time passes. And that horizon is different depending on who you are and where you are. That's hard to hold. It makes your inner map feel wobbly. The challenge is to build a new map that calms your mind without lying about how the sky works. Okay, so how did people start measuring anything close to an edge? They did it with steps. First, they measured the earth. A stick in the ground at noon at different places gives different shadows. From that, you get angles. From angles and distance, you get the size of the globe. Then they measured the moon using shadows during eclipses. Then the distance to nearby stars using parallax, the tiny wiggle in a star's position as Earth moves around the sun. Each step added a rung to a ladder. With enough rungs, you start to climb. But you can't climb to forever. At some point, the stars are too far for parallax with small scopes. So people switched tricks. They used standard candles, like certain kinds of stars that always shine with known power. If you know how bright a lamp really is, and you see how dim it looks, you can guess how far away it is. That let them reach other galaxies. And when they measured those galaxies, they saw something shocking. The farther away the galaxy, the more its light was stretched. It looked like space between us and them was growing. Not like they were flying through space away from us, but like space itself was getting bigger. This changed the idea of an edge again. Instead of a still stage with stars sliding across it, the stage itself is stretching. Now, ask yourself, if the stage keeps getting bigger and light takes time to cross it, what happens to the farthest things? Some of them slip beyond a point where their light can ever catch us, not because of a wall, but because the distance between us grows faster than their light can close it. That point, where even a beam of light can't reach you in the future, is another kind of edge. It's not the same as the edge of what you can see today. It's the limit of what you can ever see, even if you wait forever. Let's put a pin in that and go back to the story we started with. Old worlds that wanted a wall. Why did those walls last so long? Because each one answered a fear. The fear of falling off, the fear of chaos beyond the gate, the fear that things have no order. A good ceiling makes night less scary. It gives you a roof over the unknown. When you trade walls for horizons, you don't lose the need for calm. You just move it. You move calm from "I see the limit" to "I understand the limit." That's a very human shift. It's how we grow up in other parts of life too. A child wants the fence. An adult wants the map. Here's a pattern you'll hear through the rest of this series. First, a strong belief gives certainty. Second, new evidence cracks it. Third, a better frame replaces it. The trick is, the better frame is usually less simple to picture, but more simple to use. No dome, no shells on shells. Just a horizon set by time and a gentle rule. Farther means older. Oldest marks the edge. Now I'm going to do something you'll notice me do a lot. I'll give you a clean image to hold. Think of the universe as an ocean with no shore. You are on a raft with a lamp. Your light only reaches so far, and the farther it goes, the dimmer it gets. The circle where the last faint light returns is your horizon. If you swap your lamp for the first light the universe made, your horizon is the farthest anything can have sent you light since that first glow. That's your edge of sight. Let's test this picture with a few quick "but what about" questions. What about the place where the stars stop? They don't stop. Beyond the farthest galaxy you can see, there may be more. We don't see them yet, or ever, because light hasn't had time to reach us, or because expansion puts them beyond our forever reach line. That's not a wall. That's a delay. What about the place where the universe ends? If by the universe you mean everything that exists, we don't have a way to draw that boundary. If by the universe you mean the part we can see, then the edge is exactly the distance that light has travelled since the start of light, stretched by the growth of space. That edge is a number that changes as time passes. What about the beyond? Beyond our horizon, the simplest guess is more of the same. More space, more galaxies, maybe different details, but not a hard stop. That's a guess, yes, but it's a guess, guided by how the part we can see behaves. Let's go back to the people who first asked these things. Their skies were busy with stories. Hunters, birds, boats, twins. The pictures tied families to seasons. They were calendars. They were lessons. They told you when to plant, when to store grain, when to travel. When you change the frame from a roof to a horizon, you don't throw away those stories. You hang them on a larger wall. You say, this is the part we can reach, and it sits inside something bigger we can describe, even if we cannot touch it. Now here's a trick that will help you keep watching. We haven't gotten to the best part yet. The best part is the moment you realize the edge isn't far away in space. It's right here in your eyes, built into every beam you catch. And the number that tells you where it is, the number of years since the first light, shows up all through the rest of this topic. It shows up when we talk about the faint glow left from the first fire. It shows up when we talk about why the farthest galaxies look like they're racing. It shows up when we talk about why the edge today is not the same edge you'll have tomorrow. Before that reveal, let's take a small side path. It helps to know how our minds keep us hooked on simple myths. We like clean frames. Our attention rises when reality beats what we expect, and it drops when reality falls short. So if your expectation is space ends at a wall, the reality, space has a horizon set by time, can feel like a letdown unless we beat it. We beat it by showing you that a horizon is more useful than a wall. You can measure it. You can predict how it moves. You can use it to plan what to look for. And that's better than a fence that just says, stop. How to write a killer script. So, the moment we've been walking toward, the edge is two things. First, the edge of what you can see now. That's the most distant light that has had time to reach you since the universe became clear enough for light to fly freely. Second, the edge of what you can ever see. That's the line beyond which, even if you wait, light will never get to you, because space between you and it grows too fast to cross. The first moves outward with time. The second is a kind of personal event horizon. You can think of one as today's line, the other as forever's line. Here's why this matters. If you live long enough to watch deep surveys repeat, distant galaxies won't just get older in your pictures. Some will fade out of reach forever. Not because your telescope got worse, but because the universe makes some lights forever out of our grasp. That fact is bigger than a myth about a wall. It changes how you think about beyond in a real way. Let's zoom in on how the first measures began, because that's the heart of this chapter. People started with the ground. Mark a stone where the sun rises. Come back in 10 days. Mark it again. You feel the sky sliding along the horizon. That's a tiny first step to saying the sky moves. Then stack steps. Follow the shadow of a stick at noon. At different places on Earth, the length and angle change. That gives you the curve of the Earth. With the curve in hand, you can make better maps of the sky. Fast forward centuries. You're measuring star positions to tiny fractions of a degree. The far stars don't shift much as Earth goes around the sun, but the nearest ones do. That shift, parallax, lets you calculate their distance. Over time, you build a ladder. Earth size, Earth-Sun distance, distance to nearby stars, distance to star clusters, distance to nearby galaxies. Each rung depends on the last, but each also has its own way to check if you got it right. Now, bring in the part that turns the ladder into a horizon. Light's speed. It is fast, but not infinite. That single fact turns your telescope into a time machine. When you look at the moon, you see it as it was, a bit more than a second ago. The sun, 8 minutes ago. A bright star in Orion, hundreds of years ago. A galaxy in Virgo, tens of millions of years ago. The farthest faint smudges in deep images, billions of years ago. At some point, your images stop showing galaxies and start showing a smooth glow. That glow is the leftover heat from a young universe, a fog of light from when atoms first formed. Beyond that glow, light can't carry you. The fog before then was too thick. So your edge of sight today is set by the moment when the universe first became clear. That's the bright line between we can see and we can't. Let's pause and restate the problem in simple terms. The story we learned as kids, space goes on until it stops, feels neat, but doesn't predict what we actually see. The story we're building, space goes on, sight does not, predicts a lot. Why the most distant light is smooth, why very far galaxies look redder and younger, why there is a faint background glow everywhere you point a radio dish, and why your personal cosmic edge grows as time passes. We've talked about frameworks, but let's make it human again. Imagine a person standing on a shore at night thousands of years ago. They see the horizon where the sea meets the sky. They think that is the lip of the world. Now imagine another person standing on a different shore now, looking through a modern scope. They also see a horizon. The first horizon is set by Earth's curve. The second is set by time. Both are true horizons. Both are real limits to sight. Neither is a wall. That rhyme, two horizons, no walls, makes it easier to hold in your head. I promised at the start that by the end, you could explain edge in 1 minute. Here's your minute. The universe doesn't end at a fence. What ends is how far light has had time to reach us from. That line is our observable horizon. We see farther each year because light has had one more year to travel. But some places are receding from us so fast that light from them now will never reach us. That line is our cosmic event horizon. So the edge is not a place we could fly a ship to. It's a moving boundary in our view, set by time and the growth of space. Let's close the loop we opened earlier about brains liking borders. You don't have to throw away that need. Swap wall for rule. The rule is simple. Farther means older. Oldest marks the edge, and forever reach is different from today reach. The rule gives you the calm a fence once did, without making you pretend the sky is a ceiling. Before we wrap, I'm going to leave one last open loop for the next video. If the edge of sight is set by the first light that could travel freely, what is that first light? What does it look like? And how did the sky go from opaque to clear? Those answers hide in a faint glow that's still around you right now, in every direction, all the time. You can't see it with your eyes, but the story it tells is the key to turning edge from an idea into something you can test. Here's the quick recap. We started with the gut need for a wall and showed why simple ceilings once made sense. We replaced the wall with two horizons. What you can see today and what you can ever see. We tied both to time and the way space grows. We walked through how people built a ladder to reach those horizons step by step, with sticks, shadows, angles, and light. And we ended with a clear rule you can carry. No walls, just limits set by clocks and distance. This structure, hooking your curiosity, then opening and closing loops while stacking value, follows proven storytelling tricks used by top creators to keep attention. Clear click confirmation, rising payoff, rehooks between ideas, and a final peak before the close. It works because it sets expectations and then beats them with simple, vivid answers. In the early years of the 20th century, atop a mountain in California, a lone astronomer stands at the eyepiece of a great telescope, one of the largest of its time. The night sky above is pristine and alive with stars. A broad band of the Milky Way arcs overhead like a river of pale light. In the thin, cold air, the giant telescope stands poised, its machinery quiet and the surrounding darkness almost absolute. Only the faint whir of the telescope's gears and the soft whisper of night wind disturb the silence. Edwin Hubble peers into the eyepiece, aiming the instrument toward a small, hazy patch of light in the vast darkness. For generations, such faint smudges in the sky were mysteries. Spiral nebulae, they were called. Perhaps distant clouds of gas or clusters of stars within our galaxy. But on this crisp night, Hubble's patience and careful observation reveal something far more profound about the nature of the universe. Gradually, as he collects its faint light over long hours, that hazy patch of light resolves into a multitude of individual stars. It is not a nearby cloud at all. It is an entirely separate galaxy, later named Andromeda, millions of light years away. In that moment, our cosmic perspective expands dramatically. The universe, it turns out, is not just a single island of stars, our Milky Way, but is filled with countless galaxies scattered across unimaginable distances. This revelation is as startling as it is humbling. Only a few years before, astronomers had fiercely debated the scale of the cosmos. wondering whether our Milky Way was the entirety of creation, or merely one among many island universes. Hubble's discovery provided a stunning answer. The cosmos was vastly larger than anyone had imagined. Instead of a single galaxy containing all the stars, we found that there are billions of galaxies, each with its own hundreds of billions of stars. The numbers became staggering, almost beyond comprehension, and our sense of place in the universe diminished yet again. Earth was no longer at the center of anything. Not even our galaxy occupied a privileged position. It was another step in a centuries-long process of demotion, akin to when Copernicus revealed that Earth was not the center of the solar system. Like explorers glimpsing an entirely new continent beyond the edge of the known world, humanity suddenly faced an expanded horizon. Our Milky Way was just one island in a limitless cosmic ocean. In one sweep, Hubble showed that the universe contained myriad galaxies beyond our own, each a stellar city in the void. It was as if the universe had suddenly grown exponentially in size. We realized Earth's place was incredibly small, a tiny world orbiting an ordinary star in just one galaxy among countless others. The scale of creation had grown beyond imagination, and it profoundly changed our view of ourselves. We moved from thinking our galaxy was the whole universe to understanding that it was one among billions. It's a profound shift in perspective, akin to when Copernicus removed Earth from the center of the solar system. Now, not even our galaxy was central. The universe had countless centers, or perhaps none at all. Like explorers realizing an entire new continent exists beyond the horizon, we were awed and humbled by how much larger the universe truly is. Edwin Hubble did not stop at identifying galaxies beyond our own. He soon noticed something equally extraordinary about them. As he measured the light from galaxy after galaxy, he observed that their light was subtly shifted toward the red end of the spectrum, like the lowered pitch of a siren as it moves away. This phenomenon, known as redshift, indicated that these galaxies were moving away from us. And intriguingly, the farther away a galaxy was, the more its light was redshifted, the faster it seemed to be racing into the distance. Wherever Hubble looked, nearly every distant galaxy's light carried this telltale stretch toward red. By plotting the distances and velocities of many galaxies, Hubble uncovered a remarkable pattern. Almost all galaxies were flying apart from each other, and the farther a galaxy was, the faster it receded. In 1929, Hubble published this correlation, now known as Hubble's law, and announced to the world that the universe was expanding. This finding was revolutionary. It meant that space itself was stretching, carrying galaxies apart like driftwood on an ever-widening sea. In every direction, the fabric of the cosmos was stretching. As space expands, the light crossing it stretches too, which is why the glow of far-off galaxies arrives looking redder after its long journey. Imagine the universe as a giant balloon with galaxies dotted on its surface. As the balloon inflates, every point moves away from every other point. Alternatively, picture raisins in a rising loaf of bread. Each raisin, like each galaxy, grows more distant from its neighbors as the dough between them swells. There is no central point of expansion. Every region of space spreads apart in unison. The implication was staggering. The universe was not static or eternal in its present form, but dynamic and changing, growing larger with time. The concept of an expanding universe transformed our understanding of the cosmos. If galaxies are moving apart now, it implies they were once closer together in the past. Rewind the cosmic clock far enough, and there must have been a time when everything we see was crammed together in a single, dense state, like an egg before the hatch. This idea was the seed of what later would be called the Big Bang theory, the notion that the universe began as an incredibly hot, concentrated point and has been expanding and cooling ever since. At first, the concept of a cosmic Big Bang seemed almost unbelievable, even shocking. For centuries, the prevailing assumption was that the universe had simply always existed as it was. Now evidence suggested it had a beginning in time. Even Albert Einstein, whose own equations had hinted that the universe could expand, initially resisted the idea of a dynamic cosmos. He introduced a cosmological constant into his model of the universe to keep it static and unchanging. But when he learned of Hubble's discoveries, Einstein reportedly shook his head and called that adjustment the greatest blunder of his career. Had he trusted his equations from the start, he might have predicted the expansion of the universe before anyone observed it. Nature, it turned out, was indeed expanding all along. For the first time, humanity had evidence that the cosmos has a history, that it changes over time. The night sky was no longer a fixed, eternal canopy of lights. It was a story unfolding over billions of years. Hubble's work pulled back the curtain on a grand cosmic drama. Countless galaxies drifting apart, space stretching like an endless canvas, the entire universe in motion. It was a discovery, both exhilarating and unsettling. On one hand, it revealed a cosmos far larger and more dynamic than we had ever imagined. On the other, it raised profound questions. What, if anything, is the universe expanding into? Could there be an edge to space, or does it stretch on without end? How far does it go, and will it keep expanding indefinitely? And what does this expansion mean for the limits of our vision? How much of the cosmos can we ever hope to see? Under the quiet dome of the Mountain Observatory, Hubble's telescope had captured light that had been traveling for eons to reach Earth. Those ancient photons, collected on Hubble's photographic plates, told the story of galaxies as they were long ago. The light from Andromeda, for instance, had been journeying for over 2 million years before it finally met Hubble's eye, meaning he was seeing Andromeda as it was ages before modern humans existed. Standing on that mountaintop, peering deep into space, Hubble was also peering back in time. Every distant galaxy he observed was captured not in its present state, but in the state it was in when its light first set out across the universe. In a sense, his telescope had become a time machine, showing him ancient images from a younger cosmos. This realization, that distance in space is also distance in time, would soon revolutionize how we interpret the night sky. It set the stage for a profound insight. Whenever we gaze out at the cosmos, we are looking into the past, seeing the universe as it once was. We can never observe cosmic objects as they are right now, only as they were long ago. Look up at the stars on a clear night. You are actually peering into a kind of time machine. Light travels incredibly fast, about 300,000 kilometers per second, but not infinitely fast. At that speed, a beam of light could circle the entire Earth 7 times in a single second. Even across the relatively small distances of our solar system, light takes a noticeable amount of time to arrive. The gentle glow of the moon is actually over 1 second old by the time it reaches our eyes. The sunlight warming your face left the sun about 8 minutes ago. In fact, if the sun could magically vanish this instant, Earth would remain illuminated for about 8 more minutes, completely unaware of the change at first. This finite speed of light means that whenever we look at something far away, we are seeing it as it was in the past, not as it is right now. Every star in the night sky is, for this reason, a kind of time capsule. The nearest star beyond our Sun, Alpha Centauri, is about 4.4 light-years away, meaning light takes 4.4 years to reach us. So we see it as it was 4.4 years ago. Many other stars are hundreds or even thousands of light years distant, shining with ancient light that began its journey long before our time. When you gaze up at those stars tonight, you are actually witnessing bygone years of their history. Some of the stars twinkling above may no longer even exist as we see them now. They could have dimmed or died in the time it took their light to reach Earth, yet their departed glow still crosses the cosmos, telling the story of a past moment in that star's life. The night sky, then, is a patchwork of different eras, all visible at once, a cosmic mosaic of the past. It is a humbling reminder that the universe is not static, but a moving timeline spread out above us. This strange phenomenon works both ways. Just as we are looking out at other stars' past, an observer far away would see our past as well. Imagine a civilization on a planet tens of millions of light years from Earth, peering at us through a powerful telescope. The image of our planet they behold would not show our cities or people today, but a much earlier chapter of Earth's story. If they were, say, 65 million light years distant, they would right now be receiving the light that left Earth 65 million years ago. They might see lush forests and towering dinosaurs roaming our world, entirely unaware that those creatures vanished eons ago. In essence, the farther away you are, the further back in time you look, no matter which direction you gaze. When we extend our view beyond our Milky Way to other galaxies, the time machine effect becomes even more dramatic. The Andromeda galaxy, our nearest large neighbour, is about 2.5 million light-years away. The hazy form of Andromeda that we see tonight shows us that galaxy as it was 2.5 million years in the past, long before modern humans existed on Earth. Farther galaxies lie tens of millions, even hundreds of millions, of light-years away. The light reaching us from those galaxies set out when dinosaurs still roamed the Earth. Beyond them are galaxies billions of light-years away, so distant that their glow left on its journey before the Earth even existed. If we point a telescope at one of these remote galaxies, we are gazing at a scene from billions of years ago, when the universe itself was young. In this way, the night sky is like a time machine, with each step of distance taking us further back into history. The deeper into space we peer, the younger the universe appears in our view. We see cosmic events unfolding long before our time, galaxies forming, stars being born and dying, the universe evolving across eons. With today's most powerful telescopes, we can glimpse light from when the universe was in its infancy. But even this cosmic time window has a limit. There comes a point at the very edge of what we can observe where no signal has had time to reach us yet. Beyond that horizon, the universe remains out of sight, at least for now. Our view of the cosmos is bounded by time. Because the universe began around 13.8 billion years ago, there is a limit to how far out we can see. We cannot observe anything whose light hasn't had enough time to reach us. In effect, we live inside a giant sphere defined by the travel time of light since the Big Bang. Astronomers call this the observable universe, the region of space from which light has reached Earth since the dawn of the cosmos. It is the farthest horizon of our sight, beyond which the universe stretches out unseen. With each passing year, this boundary expands ever so slightly, as new light from a bit farther out finally arrives. This cosmic horizon is incredibly distant. In fact, while 13.8 billion years have passed, the expansion of space over that time means the farthest objects we can see today are much more than 13.8 billion light-years away. By current calculations, the observable universe extends about 46 billion light-years in every direction from us, forming a sphere roughly 92 billion light-years across. Within that immense volume, there are on the order of 1 trillion galaxies and uncountable trillions of stars. It's often said that the number of stars in the observable universe exceeds the number of grains of sand on all the beaches of Earth, an almost inconceivable number. It is a span of space and time so vast that our minds struggle to grasp it. And yet, that vast observable universe is only what we can see so far. It's important to understand that this boundary is not an edge of the universe, but simply the edge of what we can see. We have no evidence that the universe ends at our observable limit. In all likelihood, it continues far beyond, perhaps infinitely. We are like mariners on a vast cosmic ocean, surrounded by a horizon beyond which we cannot spy land. The galaxies beyond our horizon may very well exist, but their light has not reached us, and perhaps never will. They remain forever hidden, leaving us to wonder what sights and stories fill the space beyond our cosmic line of sight. Within this enormous observable realm lies everything we can ever hope to detect or study. It contains all the galaxies and clusters that make up the cosmic web, strewn across space in great filaments and voids. Determining the distances to these far-flung objects and charting their distribution has been one of astronomy's grandest undertakings. Over generations, astronomers developed methods to measure the vast distances of the universe and assembled a three-dimensional map of the cosmos, a map of our observable universe. It is astonishing that from our tiny planet we can measure and chart the universe on such scales. With the cosmic distance ladder in place, astronomers could begin the grand task of mapping the cosmos itself. How do we measure something as vast as the universe? Astronomers began with methods close to home and then extended outward step by step. The first rung of the cosmic distance ladder is parallax, the apparent shift of a nearby star against background stars when viewed from different positions in Earth's orbit. You can witness a similar effect in everyday life. Hold out your thumb at arm's length and look at it with one eye, then the other. Your thumb will seem to jump against the far background. That jump is caused by parallax. By carefully measuring a star's tiny annual wobble in the sky, 19th century astronomers could calculate its distance using simple geometry. It was astonishing proof that even the nearest stars lay trillions of kilometers away. Parallax provided our first direct sense of stellar distance, though its reach extends only to stars a few thousand light-years from Earth. To probe farther out, astronomers needed brighter beacons. In the early 20th century, Henrietta Leavitt discovered a remarkable property of certain pulsing stars called Cepheid variables. Their intrinsic brightness is linked to their pulse period. By observing the rhythm of a Cepheid's light, one can determine how luminous it truly is. Comparing that with how faint it appears from Earth reveals its distance. Much like knowing a lighthouse's wattage, and measuring its dimness tells you how far away it is. Edwin Hubble used Cepheid variable stars in the 1920s to measure the distance to the Andromeda Nebula, proving it was actually an entire galaxy far outside our own. Cepheids became cosmic mileposts, extending our reach to millions of light-years. Beyond the range of Cepheid stars, even brighter milepost markers come into play. Type Ia supernovae, titanic star explosions, blaze with nearly uniform peak brightness, briefly outshining an entire galaxy. This makes them superb standard candles for gauging distances of billions of light-years. By catching such a supernova in a distant galaxy, and knowing how brilliant it truly is, astronomers can determine how far away that galaxy must be. For the most distant galaxies of all, another technique comes into play: the redshift of their light. The expansion of the universe stretches the light from faraway galaxies toward longer, redder wavelengths. Hubble's law, the discovery that a galaxy's redshift grows with its distance, allows astronomers to turn this around and estimate a galaxy's distance purely from how much its light is shifted. Using redshift as a cosmic yardstick, alongside standard candles like supernovae, we can reach objects billions of light years away. In this way, a chain of overlapping methods, parallax, Cepheids, supernovae, and redshift, has enabled us to measure the scale of the visible universe. It is astonishing that from our tiny planet, we can measure and chart the universe on such scales. With these distance measuring tools in hand, astronomers could begin the grand task of mapping the universe. Over the past several decades, sky surveys have measured distances and motions for millions of galaxies. By aiming large telescopes at patch after patch of sky and recording each galaxy's redshift and position, scientists gradually built up a three-dimensional atlas of the cosmic landscape. One ambitious project in the early 2000s, the Sloan Digital Sky Survey, mapped the positions of nearly 1 million galaxies out to billions of light years. Each galaxy on this map became a point in space, and together these points revealed the large-scale structure of matter in the universe. What emerged from these vast mapping efforts is both beautiful and humbling. Galaxies are not sprinkled randomly through space. They form a tremendous cosmic web. On large scales, matter is arranged in filaments and sheets surrounding enormous voids where few galaxies reside. The pattern resembles a sponge or foam. Imagine soap bubbles where the soap forms thin walls, analogous to galaxy filaments, and the bubble interiors are like the great cosmic voids. Our own Milky Way, for example, drifts along one such filament in a small cluster of galaxies known as the local group. That local group is part of a bigger collection, the Virgo cluster, which itself is one section of an even larger assembly called the Laniakea supercluster. This intricate architecture spans hundreds of millions of light years and is just one region of the colossal cosmic web extending across the observable universe. And amid this immense structure, our Milky Way is just a tiny speck. Standing back and viewing the whole map, one cannot help but feel a profound sense of awe at the vastness of it all. We now have a map of everything we can see, a cosmic atlas spanning billions of light years and containing billions of galaxies. Yet even this grand map has a boundary. At the very edge of our observations, we encounter a wall of light from the early universe, a soft glow that permeates the sky in every direction. This is the cosmic microwave background, the afterglow of the Big Bang, marking the limit of our vision. It is the ancient light from a time long before galaxies, and it silhouettes the observable universe like a gentle, distant shore. To explore further outward, to go beyond this veil, we must delve into the realm of that primordial light and what lies behind it. To understand the cosmic microwave background, we must imagine the universe in its infancy. In the first few 100,000 years after the Big Bang, the cosmos was a seething hot plasma, a glowing fog of energy, electrons, and protons. Space was filled with light, but that light was trapped, endlessly scattered by free electrons in the opaque fireball. As the young universe expanded and cooled, protons and electrons finally combined into neutral atoms, mostly hydrogen, around 380,000 years after the Big Bang. Suddenly, the fog cleared. Space became transparent for the first time. All that previously trapped light was at last free to race across space. That primordial flash has been journeying for over 13 billion years since then. Along the way, it stretched into longer and longer wavelengths and cooled dramatically, becoming a faint whisper of its former brilliance. Today, it appears as a cold, feeble glow that permeates the cosmos in every direction. If our eyes were sensitive to microwaves, The entire sky would glow faintly with this ancient light, though we cannot see it without special instruments. This is the cosmic microwave background, the gentle afterglow of the Big Bang, still shining to us from the dawn of time. Remarkably, this cosmic afterglow was predicted before it was detected. By the 1960s, scientists realized that if the Big Bang occurred, the hot early universe should have left behind a cool remnant glow. In 1965, that prediction was confirmed, quite by accident. Two radio astronomers, Arno Penzias and Robert Wilson, were using a large horn antenna in New Jersey to study faint radio signals from the sky. They kept encountering a persistent hiss of microwave noise coming from every direction, day and night. At first, they suspected some kind of interference, even going so far as to evict a pair of pigeons roosting in the antenna and cleaning out the mess they left, thinking their droppings might be causing the static. But the mysterious noise persisted, steady and unrelenting. Around the same time, not far away at Princeton University, a team of physicists, led by Robert Dicke, had been searching for exactly such a signal, the leftover glow from the Big Bang. When Penzias and Wilson learned of this, the pieces fell into place. The annoying background hiss they had stumbled upon was no ordinary static at all. It was the cosmic microwave background radiation, the very whisper of the primordial fireball. What began as a puzzling annoyance turned out to be the echo of creation. This accidental discovery earned Penzias and Wilson the Nobel Prize, and it provided spectacular confirmation of the Big Bang theory. The cosmic microwave background, CMB, is extremely uniform. No matter where you point a radio telescope, you measure essentially the same weak temperature, about 2.7 degrees above absolute zero. In the 1990s, the COBE satellite first detected tiny variations, differences of only a few parts in 100,000 in this background glow. Later missions like WMAP and Planck mapped these subtle ripples across the whole sky in exquisite detail, revealing a mottled pattern of slightly warmer and cooler spots. These speckles are fossils of the universe's infant density fluctuations, the seeds from which galaxies and clusters eventually grew. Essentially, the CMB maps show us a baby picture of the universe, a snapshot of the cosmos as it looked long before stars and galaxies existed. Observations of the CMB have allowed scientists to pin down the age and composition of the universe with remarkable precision. The data confirm that the universe is about 13.8 billion years old. They also tell us that space is almost perfectly flat in geometry, and that ordinary matter, dark matter, and dark energy make up specific proportions of the cosmos. In other words, this gentle microwave glow carries a wealth of information about the early universe and the fundamental properties of the cosmos. It is a cosmic Rosetta Stone, letting us decipher the story of creation. This primordial light is the edge of the observable universe. We cannot see any farther back in time with electromagnetic waves. Before the release of the CMB, the universe was opaque, an impenetrable fog. It's as if we are looking at a curtain drawn across the very early cosmos. To probe an even earlier epoch, we would need to use messengers other than light. Physicists have theorized about a cosmic neutrino background, relic neutrinos from about 1 second after the Big Bang, or a background of gravitational waves from the universe's first fleeting moments. Future detectors may one day glimpse these whisper-quiet signals, allowing us to peer beyond the CMB curtain. But so far, the cosmic microwave background remains the final wall of light, the limit of our sight into the past. And so, we have traced the cosmos from the present day all the way back to that primordial glow. We've reached the edge of the known universe, the edge of sight, Beyond this horizon, the universe fades into tantalizing mystery. What lies outside the observable universe? More galaxies stretching onward without end. Other realms or dimensions beyond our comprehension. For now, we cannot know. The light from those hypothetical realms has not, and perhaps will never, reach us. Standing here, at this cosmic shoreline of visibility, we can only wonder about the vast ocean that lies beyond the horizon of our observations. The great unknown that awaits exploration in thought and theory. On a clear night, under a sky filled with stars, it's natural to wonder whether there's an ultimate border out there. How far does the cosmos go? Each step outward into space is also a step back in time. As we gaze at ever more distant galaxies, we are looking deeper into the universe's past. Eventually, as our view stretches to the extreme, we encounter a profound limit. Not a wall of stars or matter, but a boundary woven from time itself. No matter how powerful our telescopes become, they cannot conjure light that has not yet arrived. The universe is ancient, about 13.8 billion years old, but not infinitely so, and that finiteness places a limit on what we can see. Beyond a certain horizon, the cosmos vanishes into darkness, not because nothing is there, but because in the entire history of the universe, its light has not yet reached us. Amazingly, this journey into the past is not just an abstract idea. We can witness it directly. When astronomers point the Hubble or James Webb Space Telescope at a seemingly empty patch of sky and patiently collect light for days, a field of faint galaxies emerges. Many of those tiny, distant smudges are so far away that their glow began its journey when the universe was only a few 100 million years old. Those galaxies we see in the distance are cosmic infants, smaller and less organized than the grand spiral galaxies closer to us. Through our telescopes, we are essentially peering into the universe's childhood, watching galaxies being born and young stars lighting up the darkness at the very edge of what we can observe. This limit forms a sphere around us that cosmologists call the observable universe. One might imagine that with a 13.8 billion year age, the cosmos we see would extend 13.8 billion light years in every direction. Yet the continual expansion of space has carried those ancient light beams much farther out as they travelled. Today, the most distant light we detect comes from regions that are now over 46 billion light-years away. In total, our observable cosmic bubble spans roughly 93 billion light-years from one side to the other. A vast expanse, yet it is only a tiny portion of the whole universe beyond. Rather than a hard edge, the boundary of visibility dissolves into a foggy curtain of ancient light. Beyond the last distant galaxies and quasars, our instruments detect a faint, all-pervading glow coming from every direction. This is the oldest light that has managed to journey across space and time to reach us. It is a whisper from the baby universe itself, a soft afterglow from an era long before stars or galaxies existed. That gentle backdrop of microwave light is the final image on our cosmic film reel. Beyond it, we are confronted with a wall of time, where our story goes dark, at least in terms of light we can see. All around us, hidden in plain sight, is the afterglow of creation. If our eyes could see microwave radiation instead of visible light, the night sky would not be dark at all. It would shine with a faint, uniform glow coming from every direction. This gentle blanket of light is the cosmic microwave background, often described as the leftover afterglow of the Big Bang. It is extremely faint and cold now, just a few degrees above absolute zero. But it carries the imprint of a time when the entire universe was filled with a blazing brightness. This discovery of a soft whisper from the dawn of time forever changed our understanding of the cosmos. This faint cosmic glow was first detected in the mid-1960s, quite by accident. Two radio astronomers in New Jersey, Arno Penzias and Robert Wilson, were using a big horn-shaped antenna to study signals from space. To their puzzlement, they kept encountering a persistent hiss of microwaves coming from every direction, day and night. They checked and rechecked their equipment, even shooed away pigeons nesting in the antenna. But the noise would not go away. Little did they know, they had stumbled upon the relic radiation from the universe's birth. When word of their mysterious signal spread, it became clear that this was the long-predicted cosmic microwave background, the gentle echo of the Big Bang itself. To understand the origin of this cosmic background light, imagine the universe in its infancy. Long before any galaxies or stars, the newborn universe was an extremely hot, dense sea of particles and radiation. In the first few 100,000 years after the Big Bang, everything was squeezed together in a fiery plasma, a thick fog of charged particles and photons. Space was brilliantly illuminated, but also opaque, because light could not travel far without bouncing off electrons. The cosmos at that stage was like the inside of a star, glowing white-hot, yet hidden behind a veil. Then, around 380,000 years after the Big Bang, a remarkable transition occurred. The universe had expanded and cooled enough for the charged particles to settle down. Electrons began to attach to protons, forming neutral hydrogen atoms for the first time. This simple change had a profound effect. Space went from opaque to transparent. Like a fog lifting to reveal a clear sky, the light that had been trapped was suddenly free to stream across the cosmos. That liberated light has been traveling ever since, evolving from the fierce glow of a 3,000-degree plasma into the faint microwave glimmer we detect today. The cosmic microwave background turned out to be a goldmine of information about the early universe. Its very existence strongly supported the Big Bang theory, demonstrating that the cosmos did indeed spring from a hot, glowing state. Moreover, when scientists first mapped this background in detail, they found it was almost unbelievably uniform. The temperature was nearly the same in every patch of sky, varying by only a few millionths of a degree. In fact, it was so smooth that it took until 1992 for a satellite experiment to even detect those tiny variations at all. Those tiny irregularities, subtle lighter and darker spots in the all-sky map, are immensely important. Without those minute variations, the universe might have remained an almost featureless fog, with no stars or galaxies ever forming. They represent slight density variations in the young universe, the primordial seeds that gravity would later amplify into galaxies, clusters, and the large-scale structure we see today. In essence, the cosmic microwave background is like a baby picture of the universe, revealing both how smooth our cosmos was at birth and the gentle imperfections that would grow into everything we observe around us. Yet the very uniformity of the cosmic microwave background posed a deep riddle. How could regions of the young universe, so far apart that light from one could not possibly have reached the other in the time available, share almost exactly the same temperature? By the classical Big Bang picture, there had not been enough time for distant patches of the cosmos to even out their differences. Solving this mystery required thinking far beyond the conventional timeline. Scientists began to suspect that in the first split second of existence, the universe might have undergone an unbelievable growth spurt, an inflationary burst that stretched space at a phenomenal rate. It was as if our entire observable universe had once been a minuscule uniform patch that was suddenly blown up to cosmic scales, ensuring every region started out with the same conditions. Such a scenario could explain how the entire sky came to look so similar and how the tiny initial fluctuations were planted. It's a bold idea that takes us to the very edge of physics, and it is the next part of our journey. Picture the universe at its very earliest moment, a trillionth of a second old, or even less. In this unimaginable instant, according to the theory of cosmic inflation, a bizarre and spectacular event took place. The infant universe, which was still impossibly small, suddenly underwent an explosive expansion. Space itself swelled at a mind-boggling rate, far outpacing the speed of light. In the blink of an eye, indeed much faster, what had been microscopically tiny inflated to astronomical scales. This was the inflationary burst, a sudden blow-up of space that would set the stage for everything to come. The immediate consequence of this wild expansion was a smoothing out of the young universe. Imagine stretching a small, wrinkled patch of fabric into something vast and taut. The wrinkles disappear, leaving a flat surface. In much the same way, inflation would have ironed out any irregularities in the fabric of space. Any curvature of space-time, any clumps or variations, were blown apart and diluted until they became almost imperceptible. What remained after this burst was a universe that, on large scales, was extraordinarily flat and uniform. The cosmos had been prepped with the same temperature and conditions everywhere within our observable patch. Yet inflation did not leave the cosmos perfectly featureless. Even in that explosive moment, the jitter of quantum uncertainty was at work on tiny scales. Random fluctuations in energy, utterly minuscule variations far smaller than an atom, were present in the vacuum of the young universe. When space inflated, it took those microscopic fluctuations and blew them up to astronomical proportions. Regions that ended up ever so slightly denser or cooler than their surroundings were suddenly stretched across light years. These subtle differences were the seeds of structure in the cosmos. Over the eons that followed, gravity worked on those seeds, magnifying the slight bumps into clumps of matter. Areas with a touch more density accumulated more gas and dust, eventually giving birth to the first stars and galaxies. To this day, we can observe a fossilized outline of those primordial seeds as faint patterns in the cosmic microwave background. In this way, inflation tied the quantum world to the cosmic, linking the tiniest fluctuations to the formation of galaxies and clusters. With one bold idea, cosmic inflation answered several deep mysteries that the classical Big Bang couldn't. It provided a reason for the observed uniformity of the cosmic microwave background. Regions now far apart were once close together before inflation blew them out of contact, so they could share the same conditions. It accounted for why the universe appears so geometrically flat and balanced, rather than curved or skewed. Any initial curvature was smoothed away by the immense stretching, and it offered a mechanism for cosmic structure. Those quantum fluctuations magnified by inflation naturally explain the patchy pattern of matter we see billions of years later. In essence, inflation neatly filled in missing pieces of the universe's origin story. For now, cosmic inflation remains a theory, a well-supported one, but still awaiting the final proof. Scientists continue to search for telltale evidence that this fantastical expansion actually occurred. One promising clue would be a distinct pattern in the polarization of the cosmic microwave background, essentially a subtle signature left by primordial gravitational waves rippling through space during inflation. Experiments have been designed to look for this faint fingerprint, and although no definitive detection has been made yet, the indirect evidence for inflation's effects is strong. Over time, inflation has moved from a speculative idea to a central pillar of cosmology, because it so elegantly explains what we observe. Perhaps the most humbling implication of inflation is what it means for the size of reality. If space did inflate so enormously, then the portion of the universe we can see is likely just a minuscule fragment of the cosmic expanse. Our observable universe could be like a single grain of sand on an endless beach, a tiny patch amidst a much vaster realm we will never behold. Far beyond our cosmic horizon, space could stretch on so far that countless galaxies and other wonders remain forever unseen, carrying on in isolation from us. The universe may continue endlessly beyond the limits of what our telescopes can capture, an awe-inspiring possibility. This realization invites us to ponder those hidden realms beyond our view. What might lie out there in the vast reaches we can never observe? Throughout history, people have grappled with the idea of whether the universe has an edge. Ancient cultures imagined physical boundaries, a literal edge of the world, or a dome over the sky. Even a century ago, many wondered if there was anything beyond our Milky Way galaxy, or if our galaxy was the entirety of the universe. That changed when astronomer Edwin Hubble proved that spiral nebulae were actually other galaxies far outside our own, expanding the known cosmos by orders of magnitude. As our telescopes improved, we kept discovering more galaxies strewn farther out in space, with no sign of a stopping point. It became clear that the universe extends far beyond what we once imagined. Today, we understand that space itself likely has no abrupt edge. Instead, the limitation is how far we can see or travel. When we talk about realms beyond our cosmic horizon, we're not implying an edge or a wall at the end of space. All indications suggest that the universe extends far beyond what we can see, and perhaps it goes on forever. The large-scale geometry of space appears flat, which hints that it could be infinite, or at least so vast that any curvature is undetectable. And even if the cosmos were somehow finite, it wouldn't have a hard boundary in the conventional sense. Space could be curved back on itself like the surface of a sphere, meaning you could travel in one direction indefinitely without ever encountering a literal edge. In either case, our observable universe is likely just one small window into a much larger, possibly endless, expanse. As far out as our telescopes gaze, we see galaxies scattered across space, forming clusters and filaments that weave a cosmic web. This grand structure does not abruptly stop at the edge of what we can observe. There is no thinning of galaxies or fading of matter as we approach the horizon of visibility. Instead, every indication is that if we had a way to see further, we would simply unveil more of the same tapestry. Additional galaxies, stars, and intergalactic voids stretching onward. The universe beyond our horizon likely looks much like the universe we know, following the same physical laws and patterns, just extending into regions we will never be able to observe directly. It's important to remember that the cosmic horizon is an observer's limit, not a physical barrier in space. An astronomer living in a galaxy billions of light years away would have their own observable sphere, overlapping with ours, but also encompassing regions we cannot see. From their perspective, they would see galaxies that lie beyond our horizon, just as there are galaxies at the edge of our view that lie beyond theirs. No single observer can see the entirety of the cosmos. Each can only see a bubble of space-time determined by their position and the universe's age. This relativity of perspective reinforces the idea that much more exists than any one vantage point can reveal. The sheer scale of what might lie beyond is mind-bending. If the universe truly is infinite, then it carries some astonishing implications. In an infinite expanse, Every possible arrangement of matter that can happen will happen somewhere. That means far beyond our horizon, there could be regions with stars and galaxies arranged in completely different ways than what we see around us. There might even, purely by chance, be distant patches of the universe that end up looking somewhat like our patch. Perhaps with a galaxy much like the Milky Way, or even an Earth-like planet with familiar landscapes. These possibilities sound like science fiction, and indeed they are speculative, but they serve to highlight how limitless an infinite cosmos would be. We will likely never have direct evidence of what lies beyond our observable bounds. No matter how powerful our telescopes become, or how far future explorers might travel, the regions outside our cosmic light horizon are sealed off by time and distance. It is a strange feeling, a frontier that we cannot and will not ever cross, not because of a lack of technology, but because of the fundamental limits of the universe itself. This realization is both humbling and poignant. There are, right now, countless galaxies filled with stars and wonders that will remain forever invisible to us. We know they are almost certainly there, yet they are beyond our reach, existing in a permanent twilight beyond the cosmic horizon. In a sense, our cosmic horizon is like an event horizon, the kind of boundary we encounter around a black hole. Just as nothing that crosses a black hole's event horizon can ever return or be seen from the outside, anything beyond our cosmological horizon is effectively cut off from us forever. We can think of it as the universe's own point of no return for information. To explore this idea further, it helps to delve into the parallel with black holes and their horizons, and what it really means to have a cosmic event horizon. To understand the nature of our cosmic event horizon, it helps to recall how a black hole's event horizon works. A black hole, formed from a collapsed star or other mass, has gravity so intense that beyond a certain boundary, not even light can escape its pull. This boundary is the event horizon, a one-way membrane in space. Once anything drifts past that invisible line, it vanishes from the observable universe, at least from the perspective of an outside observer. It's not that an object ceases to exist, but any light or information from it is trapped, unable to ever reach us. The event horizon is essentially a point of no return. Our universe has an analogous boundary, not caused by gravity pulling in, but by space itself rushing out. In the late 20th century, astronomers discovered that the expansion of the universe is speeding up, driven by a mysterious something we now call dark energy. This accelerated expansion creates a cosmic event horizon. There comes a distance beyond which space is expanding so quickly that light emitted there can never catch up to us. Just as a swimmer might struggle against a swift current and never make it to shore, photons from extremely distant galaxies struggle against the expansion of space and fall behind. Beyond a certain point, the expansion outruns even light's ability to travel, and so any events happening in those far regions are effectively cut off from our view forever. At present, this cosmic event horizon is estimated to be about 16 billion light-years away. In other words, if a galaxy is farther than roughly that distance from us right now, any light it emits today will never reach Earth, no matter how long we wait. Surprisingly, some of the galaxies we can see in telescopes today are already beyond this event horizon. How can that be? The answer is that we are seeing those galaxies as they were billions of years in the past, when they were closer to us. Over time, the relentless expansion has since carried them farther away, to the point that light leaving them now is stranded, unable to bridge the ever-widening gap. We are effectively observing a fossil light from those galaxies, a final snapshot of their ancient past. Any present-day events transpiring in those remote galaxies will remain forever unknown to us. The concept of a cosmic event horizon also carries profound implications for the far future of our universe. As cosmic expansion continues, more and more galaxies will gradually slip beyond the horizon. Billions of years from now, distant galaxies that we can currently observe will fade away, redshifted into obscurity. Trillions of years into the future, an observer in our galaxy, or what remains of it, might find the sky nearly empty, with only the faint glow of a few neighboring stars or galaxies that are gravitationally bound to us. Essentially, our local group of galaxies could become an island in a dark, silent ocean of space. All evidence of the wider universe, the clusters, the cosmic microwave background, the great web of galaxies, will have vanished from view. Future astronomers, if any exist, might have no way to know of the rich cosmos that once lay beyond, because the light telling those stories will no longer be arriving. It paints a lonely picture of a far future cosmos, a universe that appears quiet and empty, with its earlier fireworks hidden forever behind an unreachable horizon. This cosmic event horizon not only limits what we can see, but also where we can send information. Even if there were distant observers beyond that boundary, our radio messages or spacecraft could never reach them. Each pocket of the universe becomes an isolated chapter, unable to share its story with others, once separated by this expanding gulf. Faced with these fundamental limits of light and distance, astronomers are looking to other, more exotic forms of cosmic messengers. Perhaps there are ways to sense the invisible, to detect traces of the universe beyond the reach of ordinary light, using phenomena that don't obey the same constraints. The story of the cosmos is written in more than just light. For generations, astronomers relied on electromagnetic radiation, from visible starlight to radio waves and X-rays, to observe the universe. But there are limits to what light can reveal. Some parts of the cosmos are shrouded in dust or gas that light cannot penetrate. Other vital clues were emitted in forms that are not light at all, or in eras before any light could escape. To truly extend our vision beyond these limits, scientists have begun to use new kinds of eyes and ears, detecting cosmic messengers that were long invisible to us. One such messenger is the ripple of space itself, gravitational waves. Predicted by Einstein's theory of general relativity, these are vibrations in the fabric of spacetime, produced by some of the most violent events in the universe. For decades, they were purely theoretical, but in 2015, scientists made a historic detection. Twin black holes merging in a distant galaxy announced their collision not with light, but with a fleeting shudder of spacetime. Instruments like LIGO measured this faint ripple as it washed over Earth, the first direct sound ever heard from the cosmos. Unlike light, gravitational waves pass through matter almost unhindered, carrying information from places that would otherwise be hidden. They can emerge from deep inside exploding stars or from the hearts of merging black holes, realms that light cannot escape. They might even carry echoes of the universe's first moments. By listening to these gravitational whispers, we open a new window onto events that were once beyond the reach of any telescope. Scientists are especially eager to find gravitational waves left over from the Big Bang itself. These primordial waves would be incredibly faint, like an almost imperceptible background hum, but detecting them would be revolutionary. It would allow us to glimpse the universe when it was less than a second old, a time utterly beyond the reach of any electromagnetic signal. Several experiments are searching for subtle patterns in the cosmic microwave background and in space itself that might betray the presence of these ancient gravitational tremors. Should we succeed, it would be as if we tuned in to the faint echoes of creation. Another set of elusive messengers are neutrinos, nearly massless, ghostly particles that zip through space and through matter with ease. Produced in enormous quantities in nuclear reactions, neutrinos stream straight out of places where light struggles to escape. For instance, the core of our Sun emits neutrinos that rush out and reach Earth in seconds. By contrast, light from the Sun's core takes tens of thousands of years to work its way out. When a massive star collapses in a supernova, a flood of neutrinos bursts from the star's heart, heralding the explosion even before any light escapes. In 1987, detectors on Earth captured neutrinos from a supernova hours before the first light was seen. It was striking proof that neutrinos can carry news from the core of a cosmic catastrophe while light remains trapped. Because neutrinos barely interact with anything, they can cross dense clouds and immense distances virtually unimpeded. This makes them exceptional informants about events and environments that would otherwise remain hidden. And then there is dark matter, the unseen mass that outweighs all the stars and galaxies we can see. Dark matter neither emits nor absorbs light, rendering it effectively invisible. Yet its gravity sculpts the universe. Galaxies spin faster than their visible matter alone can account for, and clusters of galaxies hold together only thanks to the gravitational pull of vast halos of dark matter. Astronomers have learned to map this hidden mass by observing how its gravity bends the light of distant objects, a phenomenon called gravitational lensing. Through lensing, we visualize colossal clouds of dark matter surrounding galaxies and spanning between them, revealing an immense cosmic scaffolding that light could never show. One famous example is the Bullet cluster, where two colliding galaxy clusters showed the normal matter, seen in X-ray light, being wrenched apart, while the bulk of the mass, dark matter, sailed through and was detected only by its gravitational effects. It was dramatic confirmation that most of the matter involved was invisible. By studying the distribution of dark matter, we uncover the shadow structure of the cosmos, the underlying framework on which galaxies form and evolve. Scientists around the world are also trying to detect dark matter particles directly in deep underground labs, hoping for even a whisper of interaction. If they succeed, it could open a new window on the early universe and on physics beyond our current knowledge, revealing secrets from the hidden side of nature. Indeed, dark matter holds keys to a chapter of the cosmic story that we are only beginning to decipher. By combining all these new messengers with traditional astronomy, we are at last peeling back more layers of the cosmic mystery. Gravitational waves, neutrinos, and the mapping of dark matter have expanded our senses beyond vision, allowing us to experience the universe through sounds and phantom particles, as well as light. With each breakthrough, we illuminate a bit more of the previously invisible universe. Where once we faced a wall of darkness, we now find windows, subtle but real, that give us glimpses of what lies beyond. Our cosmic horizon, both in space and time, has begun to broaden. Even so, there will always be further depths shrouded in mystery, beckoning us onward. The more we learn, the more the universe invites us to keep exploring, to keep asking what lies beyond. Drifting in the silent vastness between distant galaxies, we sense a presence beyond the light we know. The last glimmers of familiar starlight fade behind us, and an even deeper darkness unfolds ahead. Far from any sun or nebula, the view is an inky void, dotted only with faint glimmers of faraway galaxies. The silence is absolute, a deep quiet, broken only by our own thoughts. At first glance, it feels as though nothing exists out here, aside from those distant island universes scattered across the darkness. Yet as we float further into the cosmic abyss, a subtle influence makes itself known, an invisible pull that tugs on galaxies and starlight alike. We begin to realize that the darkness itself is alive with unseen matter and energy, quietly orchestrating the grand dance of the cosmos. For centuries, the universe appeared to us as nothing more than islands of light adrift in a sea of blackness. It was thought that if something did not shine or emit a signal, then it simply wasn't there at all. Darkness was assumed to be mere empty void. But as the 20th century dawned, astronomers began to suspect that this black cosmic ocean was not truly empty after all. And indeed, in the 1930s, a curious observation hinted at an enormous secret hidden out in that void. In 1933, the Swiss-American astronomer Fritz Zwicky, while studying a distant cluster of galaxies, made a startling discovery. He found that the galaxies in this cluster were moving far too fast to stay bound together by the gravity of their visible stars alone. By all rights, they should have scattered off into space long ago. Yet, the cluster was somehow holding firm against this centrifugal dash. There had to be a tremendous amount of unseen mass providing the necessary gravity, far more than all the shining galaxies he could see combined. Zwicky dubbed this unseen mass dunkel materia, or dark matter, an invisible substance lurking out in the cosmic dark, weighing down the universe like a hidden anchor. For decades, the notion of dark matter lingered at the fringes of astronomy. Intriguing, but unconfirmed. It wasn't until the 1970s that compelling new evidence emerged, quietly but unmistakably, from the graceful swirls of spiral galaxies. Astronomer Vera Rubin devoted herself to measuring how fast stars orbit around their galactic centers. In a spiral galaxy like our Milky Way, one would expect the outermost stars to orbit much more slowly than those near the center, much as distant planets move more sluggishly around the sun. But Rubin discovered something astonishing. Stars far out in the galaxy's suburbs were moving just as fast as those near the brilliant core. The outer regions of these spirals were spinning too swiftly to be held in place by the gravity of the visible matter alone. Once again, the conclusion was unavoidable. There must be more matter out there, an enormous amount of mass that emits no light, enveloping each galaxy in a vast, hidden halo. Rubin's groundbreaking work confirmed that this dark material was no mere anomaly, but a fundamental component of galaxies, a discovery that forever altered our understanding of the cosmos. Bit by bit, the evidence for this unseen mass continued to mount. Galaxies in clusters rattled around, as if bound by an invisible gravitational glue far greater than what their stars and gas could supply. Individual galaxies behaved as though cocooned in halos of heavy, unseeable matter, like fireflies caught in jars of pure glass, the container invisible but confining their flight. Even light itself revealed the dark presence. Distant galaxies appeared distorted, stretched into arcs and rings by the gravity of massive concentrations along the line of sight that emitted no light of their own. This phenomenon, known as gravitational lensing, showed that huge clumps of matter were bending light in the depths of space, even when telescopes revealed nothing visible in those places. In certain cases, gravitational lensing produced spectacular visuals, elegant rings of light called Einstein rings, or multiple images of a quasar arranged in an Einstein cross, all created by the gravity of some unseen mass in front. More often, the distortions were subtle, tiny stretches and shears in the shapes of background galaxies. By carefully analyzing these distortions in countless distant galaxies, astronomers could map where the hidden mass lay. It's akin to standing on a hill at dusk and inferring the presence of invisible valleys and mountains by how they redirect rolling balls or beams of light. Using this approach, scientists drew detailed maps of dark matter in galaxy clusters and on larger scales, tracing the otherwise invisible cosmic web. These techniques revealed that every galaxy sits within a broad halo of dark matter, and that filaments of dark matter lace the universe just as our theories predicted. In this way, gravitational lensing helped transform dark matter from a hypothesis into a mapped reality woven throughout the cosmos. One particularly striking piece of evidence for dark matter came from a cosmic collision observed in the early 21st century. Astronomers studied a system called the Bullet Cluster, where two clusters of galaxies had crashed into one another at tremendous speed. In the aftermath, the clouds of hot gas from each cluster, which comprise most of the normal matter visible in X-rays, were left behind, slowed by the titanic impact. But the stars and galaxies, and crucially the unseen mass, passed through the collision almost unimpeded. Using gravitational lensing to map the mass, scientists found that the bulk of the cluster's gravity was not centered on the visible gas at all, but had moved ahead with the unseen dark matter. It was a dramatic confirmation. The invisible dark matter had separated from the ordinary matter, unmistakably revealing its existence and behavior. In one cosmic event, nature had separated the seen from the unseen, allowing us to witness dark matter's role laid bare. This hidden mass pervades the cosmos, silently governing the movements of galaxies and the growth of structure. Dark matter neither emits nor reflects light. It slips through us unnoticed, like a ghost in the darkness. And yet, without it, the universe we know could not have formed in the way it did. Galaxies were able to assemble and remain intact thanks to the gravitational scaffolding provided by this unseen matter. Long before stars first ignited, clumps of dark matter were drawing in ordinary gas with their gravity, providing seeds for the first galaxies. Over billions of years, dark matter continued to shepherd cosmic evolution, its gravity pulling galaxies into clusters, keeping those galaxies from flying apart as they spun, and guiding the emergence of ever larger structures. Unseen and unfelt except by its pull, this dark companion has been the silent architect of the cosmos on the grandest scales. Floating in our imagination just outside a spiral galaxy, we picture the scene. A great disk of starlight shining in the void, surrounded by an enormous halo of something completely dark. That halo of dark matter extends well beyond the visible edge of the galaxy, like a vast cocoon. If it were faintly aglow, the galaxy would appear many times larger, but instead this halo is utterly transparent. Only its gravitational effect betrays its presence, gently tugging at stars and bending the path of passing light. Our own Milky Way is one such galaxy, embedded in an invisible halo that far outweighs all its visible stars. The shimmering band of the Milky Way we see arching across our night sky is just the glittering embroidery on an enormous cloak of darkness. Dark matter's influence stretches far beyond individual galaxies. From our vantage point, drifting between galaxies, we sense that these islands of light are not scattered randomly through space. There is a pattern, a faint structure connecting one galaxy to another across the cosmic sea. Through the gravitational tug of dark matter, galaxies are drawn together in great filaments and sheets, and between those structures lie immense spaces, nearly devoid of matter. Out here in the intergalactic expanse, the darkness is not uniform emptiness, but part of a grand design shaped by the hidden mass. The stage is set to explore the larger architecture that dark matter has woven through the universe, an enormous scaffold of unseen threads that holds the galaxies in its web. On the largest scales, the universe reveals a breathtaking tapestry, often called the cosmic web. Imagine a spider's web stretched across the cosmos, but made of invisible threads that only become apparent by the galaxies strung along them like dewdrops. In the depths of intergalactic space, where darkness seems absolute, these filaments of dark matter form highways of gravity, guiding the assembly of clusters and superclusters of galaxies. Each thread of this web can span hundreds of millions of light years, and where the threads intersect, matter has pooled into enormous clusters containing thousands of galaxies. We drift along one such filament in our mind's eye, moving through a nearly imperceptible bridge between clusters. Wisps of gas accompany the dark matter filament, and embedded in those wisps are galaxies like tiny lanterns, marking our path through the void. In this way, the cosmic web threads the universe together, connecting the islands of light across the darkness in one immense, interconnected network. The cosmic web was born in the universe's youth, when everything was hot, dense, and nearly uniform. In that primordial era, there were tiny imperfections, slightly denser spots that gravity gradually pulled into thicker clumps. Dark matter, though invisible and mysterious, responded to these slight variations, drawing itself into knots and strands over billions of years, with no pressure or light to oppose it, since dark matter interacts so feebly with anything except gravity. It collapsed readily into an intricate scaffold that ordinary matter later traced. As normal matter cooled and formed atoms, it fell into the gravitational wells provided by dark matter. Where dark matter had accumulated into filaments and halos, gas gathered and ignited into stars. Galaxies took shape like glitter along those dark strings, illuminating the underlying structure we otherwise could not see. Over time, these galaxies merged and grew. Clusters of galaxies formed at the dense junctions of the web, all orchestrated by the vast hidden skeleton of dark matter. Our own galaxy is part of this vast network. The Milky Way, along with our neighbouring Andromeda galaxy and a swarm of smaller satellite galaxies, inhabits a filament of dark matter that winds through our local cosmos. This filament connects to larger nodes, the nearby Virgo cluster of galaxies, for instance, much like a strand of cosmic silk linking beads of light. If we could zoom way out and view the universe from a great distance, we would not see galaxies sprinkled randomly. Instead, we'd behold a pattern resembling a gigantic cosmic foam or a web, luminous clusters of galaxies dotting the junctions of gossamer filaments, and immense dark voids yawning in between. Bright clusters of galaxies stand out at the intersections of translucent filaments, and vast cosmic voids appear as the gaps in between. It is a sobering, humbling image. Most of the universe's grand design is drawn in darkness, sketched by an invisible hand. What we see, the galaxies glowing here and there in the void, are merely traces of a deeper structure. Beyond those luminous threads and nodes lies an even greater darkness, the enormous voids that stretch between the filaments, where galaxies are exceedingly scarce. Decades ago, when astronomers first began to chart the positions of galaxies, they were astonished to find that galaxies were not evenly spread through space as one might expect. Early galaxy maps revealed immense structures, sprawling filaments and sheet-like walls of galaxies separated by enormous empty gaps. One of the first such features discovered was nicknamed the Great Wall, a chain of galaxies hundreds of millions of light-years long. Next to it, astronomers found an immense void, a gigantic region with far fewer galaxies than anticipated. These early observations were the first direct glimpse of the cosmic web's existence, confirming what theories and computer simulations would later show in vivid detail. As we float onward through this large-scale structure, we find ourselves approaching one of the great cosmic voids that lie between the filaments. The transition is subtle. One by one, the surrounding galaxies grow more sparse and dim. the guiding filament we followed thinning and fading behind us. Soon we are drifting in a volume of space so vast and so empty that galaxies exist only as a few distant glimmers on the far horizon. We have entered a true cosmic void, an enormous realm stretching tens or even hundreds of millions of light years, where there are almost no galaxies at all. The silence here is profound. If we imagine standing somehow in the middle of this void, we would see nothing but darkness in nearly every direction, save perhaps for the faint pinprick of a few galaxies incredibly far away. The surrounding walls of the cosmic web are so distant that to any observer inside, the void appears nearly empty, the universe reduced to a sparse scattering of faint, unreachable lights. In such infinite quiet and darkness, one might truly feel the vast loneliness of the cosmos. These empty spaces are among the largest structures in existence, though calling them structures is a bit ironic, since they are defined by absence. One famous example, the Boötes Void, has been nicknamed the Great Nothing. It spans roughly 300 million light-years across, yet within that tremendous volume, astronomers have found only a few dozen galaxies. By comparison, a region of that size in a typical part of the universe might contain tens of thousands of galaxies. To float in the center of the Boötes Void is to experience a solitude beyond anything on a human scale, surrounded by a darkness almost complete. The nearest galaxy could be tens of millions of light-years away or more, so distant its light would be unimaginably faint. In such a place, the night sky of any hypothetical traveler would contain no familiar constellations, no faint band of a Milky Way, only an almost unbroken black, perhaps punctuated by one or two far-off galaxies barely visible to the eye. Cosmic voids like this are not entirely devoid of matter. There are still trace particles drifting through them, a thin haze of atoms, perhaps a few per cubic meter. And these voids do contain dark matter, though at an even lower density than elsewhere. By human standards, however, they are truly vast emptinesses. These are the spaces between the filaments of the cosmic web, enormous cosmic oceans separating the continents and islands of galaxies. How such immense voids came to be is understood as part of the same process that built the cosmic web itself. Regions that started out slightly emptier than average in the early universe gradually became even emptier as gravity drew matter into the denser regions, like water draining away from shallow puddles into deeper wells. Over billions of years, smaller voids merged into larger ones, just as soap bubbles coalesce into a bigger bubble, leaving some stretches of the universe nearly bare. In fact, cosmic voids now occupy most of space itself. The luminous cosmic web is only a thin lattice outlining these tremendous gaps of nothingness. Traveling through such a void, one truly confronts the meaning of cosmic solitude. For endless millennia, one could voyage in darkness and not approach another galaxy. Yet even as these voids represent an absence of light and matter, they too play an important role in the cosmic story. Their emptiness was the flip side of structure. It allowed matter elsewhere to collect into galaxies and clusters, and the voids themselves offer subtle clues in their very nothingness, the way light travels across them, or the way the universe's expansion progresses within them, provides hints about the forces at work on the largest scales. Indeed, empty as the voids are of matter, they may be filled with something even more mysterious, something that doesn't clump into galaxies or stars at all, but instead is woven uniformly into the fabric of space and drives galaxies apart. This brings us to one of the most profound discoveries in cosmology, the realization that even the emptiest stretches of space are not truly empty, for space itself carries an energy that shapes the destiny of the universe. Not long ago, astronomers expected that the expansion of the universe, set in motion by the Big Bang, would gradually slow down. It seemed logical that the collective gravity of all the matter, visible and dark, would put the brakes on cosmic expansion over time. Many thought the expansion might even halt one day and reverse into a collapsing big crunch, or at least continue forever, but ever more slowly. By the late 20th century, determining the fate of the cosmos had become a major quest in astronomy. As the 1990s drew to a close, two independent teams of astronomers were observing distant exploding stars known as Type Ia supernovae. These brilliant stellar detonations serve as standard candles. Their true brightness is known, so how faint they appear indicates their distance. By measuring supernovae in faraway galaxies, scientists could gauge how the universe's expansion had proceeded over time. The expectation was that these distant supernovae would appear a little brighter than expected in a uniformly expanding universe, meaning the expansion had been slowing under gravity's influence. Instead, the teams found the opposite. The supernovae were dimmer, farther away than anticipated. The expansion of the universe was not slowing down at all. It was speeding up. This discovery landed like a thunderbolt in cosmology. Some force or effect was overwhelming gravity on the largest scales, pushing galaxies apart faster and faster as time went on. Scientists named this mysterious phenomenon dark energy. The term reflects our ignorance. Much as dark matter is dark because it emits no light and remains hidden, dark energy is dark because its nature is deeply mysterious. We cannot see or touch it, but we infer its existence from its startling effect on the cosmos. It appears to be an intrinsic property of space itself, an energy woven into the very fabric of the vacuum. As space expands, more of this energy emerges, driving expansion even harder in a self-reinforcing cycle. Dark energy now dominates the cosmic ledger. According to the best measurements, roughly 68% of the universe consists of this dark energy. Dark matter, that invisible mass holding galaxies together, makes up about 27%. And all the ordinary matter, the stars, gas, dust, planets, and living beings, amounts to less than 5%. In other words, everything we have ever directly observed is only a minor constituent of the cosmos. The vast majority comes in two shadowy forms, one that pulls, dark matter's gravity, and one that pushes, dark energy's expansion. It is humbling to realize that the fate of the visible universe is controlled by entities we have never seen directly. So what exactly is dark energy? In truth, we do not yet know. One possibility is that it is the cosmological constant first proposed by Albert Einstein, a kind of constant energy of the vacuum, an unchanging property of space itself. Einstein originally introduced such a term in his equations to balance gravity and allow for a static universe. When cosmic expansion was discovered, he reportedly called that term his biggest blunder, only for it to be revived decades later as a leading explanation for dark energy. If dark energy is indeed a built-in property of space, then as the universe expands, space simply brings more of this energy into being, and the effect never fades. Another possibility is that dark energy is some dynamical field that can vary over time and space, something like a ghostly cousin to the fields that give particles like photons and electrons their behavior. Some have even suggested it hints at new physics entirely, perhaps extra dimensions of space, or a flaw in our understanding of gravity when applied on the grandest scales. For now, all we can say from observations is how dark energy behaves. It acts as if it has negative pressure, pushing outward on the fabric of space. This idea that the void of space could harbour energy and exert a repulsive force is deeply counterintuitive. Yet the evidence suggests that emptiness itself is driving the cosmos apart. The presence of dark energy means the universe's expansion, far from slowing, is actually accelerating into the future. Galaxies distant from each other are being carried away at increasing speeds as space between them stretches. Over vast spans of time, this will profoundly alter the cosmos we observe. As dark energy pushes the cosmic fabric further and further, distant galaxies will recede beyond our ability to ever see them again. The sphere of the observable universe, our cosmic horizon, will shrink as more and more galaxies speed out of view. Millions, then billions of years from now, an observer in our galaxy, or its remnant, will look out and see fewer and fewer galaxies, until perhaps only the nearest ones remain visible. The universe will appear emptier and darker, not because those other galaxies cease to exist, but because they have been driven so far away that their light no longer reaches us. It was a profound revelation. A force woven into empty space was dictating the universe's fate. Our conception of the cosmos had to change, for even the void was found to wield a mighty influence. Suddenly, the vacuum itself was no longer truly void. It had become a kind of hidden dynamo, quietly shaping the cosmos on the grandest scale. This realization transformed our understanding of the universe's evolution. The ultimate question then arises: what is the fate of the cosmos? Will this accelerated expansion continue forever? Or are other finales possible? Astronomers and physicists have pondered a few grand scenarios. One possibility is an outcome often called the Big Freeze, or heat death, in which expansion goes on indefinitely. In this vision, the cosmos expands eternally, growing ever colder and darker. Galaxies drift farther and farther apart. As time passes, star formation within galaxies grinds to a halt. The reservoirs of gas needed to birth new stars get used up or become too diffuse. Existing stars burn out one by one. Trillions of years from now, the last stars will wink out, leaving behind only faint stellar embers. White dwarfs cooling into black dwarfs, neutron stars, and black holes. In an ever-expanding universe with unrelenting dark energy, even those black holes will not last forever. Given enough time, they will evaporate through a process known as Hawking radiation, a slow leakage of particles from a black hole's edge, vanishing over incomprehensible eons. If even the very protons inside atoms are unstable over extremely long timescales, then eventually matter itself will disintegrate, atoms decaying into faint whispers of radiation. What remains then is a thin, cold haze of particles and photons, spread so dilute that for any given volume of space, there is virtually nothing in it. The temperature of the universe creeps ever closer to absolute zero. In this scenario, the cosmos fades into an eternal, quiet darkness, a final state in which nothing new happens, because no free energy remains to drive change. Over unimaginable expanses of time, all traces of activity cease, leaving the universe in a state of perpetual stillness. This heat death of the universe is a melancholy thought. A universe that was once bright and young, full of galaxies and stars, eventually becomes an endless night, cold and silent. Yet other potential endings have been imagined. If dark energy were to grow even stronger over time, a scenario dubbed the Big Rip, then the repulsive force would increase without bound. It could grow so powerful that it overcomes not just the gravity between galaxy clusters, but eventually the gravity holding galaxies together, and even the forces binding atoms. In such a fate, there would come a time when galaxies themselves are torn apart. Stars would be flung outward from their galaxies. Planets would drift away from their stars. And as the acceleration kept increasing, even solar systems would be shredded, and then stars and planets themselves would be ripped to pieces. In the final moments, the very atoms, the nuclei and particles, might be sundered by the runaway expansion of space. the universe would meet a catastrophic end, disintegrating everything. Even spacetime itself might be rent asunder. Thankfully, current observations suggest this big rip scenario is unlikely. Dark energy, as best we can tell, does not seem to be growing stronger in this manner. It behaves more like a steady property of space, similar to Einstein's cosmological constant, than a force that increases without limit. Another possibility, once seriously considered, is the opposite of eternal expansion. A cosmos that stops expanding and reverses into a collapse, the Big Crunch. Before the discovery of dark energy, astronomers tried to measure the density of matter to see if gravity might eventually halt the expansion. If there were enough matter in total, gravity would gradually slow the expansion, bring it to a stop, and then pull everything back inward. If that were the case, billions of years in the future galaxies would begin to rush back together. Distant galaxies would come into view again as they converged. Eventually, all galaxies and clusters would coalesce. The universe would grow hotter and denser as everything crowded together. Ultimately, all matter and energy might collapse into an unimaginably hot, dense state, perhaps even into a single point, essentially the Big Bang in reverse. Some speculated that such a big crunch could potentially trigger another Big Bang, an oscillating universe that cycles through expansions and contractions endlessly. However, given the influence of dark energy that we observe now, this scenario appears very unlikely. There simply isn't enough gravity, even with all the dark matter, to overcome the outward push of dark energy. The scales are tipped in favor of unending expansion, not collapse. Thus, as far as we can discern, the most plausible fate is an ever-expanding universe heading toward cold and darkness. It's a vision of slow, inexorable change, a long twilight that deepens into night over trillions of years. Still, we must admit that our understanding is incomplete. Dark energy itself is an enigma. If its properties were to change in the far future, the fate of the universe could change with it. Some entirely new physics, something we have yet to discover, might intervene on cosmic timescales. The universe has surprised us before. It may surprise us again. For now, though, the best evidence points to a cosmos that expands forever, its brilliant early era giving way to an old age of darkness and silence. Even as we peer into the distant future, straining to imagine eons to come, we are reminded of how much we have learned by studying the darkness between the stars, rather than just the stars themselves. The hidden mass of dark matter and the unseen push of dark energy were revealed to us, not through direct sight, but through subtle influences on the cosmos. Our journey through this darkness between would not be complete without considering how we know these shadowy components exist at all. After all, if dark matter is invisible and dark energy untouchable, how can scientists study them? The answer is that we have learned to listen to the universe in new ways, detecting the faint whispers and echoes of the unseen. Imagine a vast, utterly dark room furnished with invisible objects. You cannot see them directly, but you might discern them by how they affect the things you can see. Perhaps by noticing a beam of light bend around something hidden, or by feeling an unseen tug on a moving object. In much the same way, astronomers map the invisible by observing its influence on the visible. One powerful method uses the universe's own brilliant beacons, distant galaxies and quasars whose light travels billions of years across space. When that light passes near a massive object, say a cluster of galaxies rich in dark matter, the light's path is curved by gravity. To us, the background object's image may appear stretched or even multiplied, as though a cosmic lens is warping and magnifying it. This phenomenon, gravitational lensing, has become a crucial tool for seeing dark matter, as we noted earlier. By examining the subtle distortions in countless background galaxies, scientists infer where hidden mass lies along the line of sight. It's like reading the pattern of ripples in a pond to discern that an invisible stone lies beneath the surface. Using this technique, we've managed to outline the great invisible structures, mapping the dark matter in clusters and even the large-scale filaments, thereby visualizing the scaffolding of the dark universe. Each distorted galaxy image is a whisper of gravity, telling us where the unseen mass resides. Another approach involves conducting huge surveys of galaxies across space and time. By mapping the three-dimensional positions of millions of galaxies, we can see the cosmic web traced by their distribution. Large surveys, for example, the Sloan Digital Sky Survey, have given us detailed maps showing filaments and voids spanning vast distances. These maps of galaxy clustering serve as a negative image of the dark matter structure, since galaxies gather where dark matter created potential wells. When cosmologists compare these observations with computer simulations of structure formation, they find excellent agreement, but only if the simulations include the right mix of dark matter and dark energy. Adjust the amounts of these dark components, and the pattern of galaxies in the simulated universe changes. The fact that one specific mix, roughly 27% dark matter, 68% dark energy, makes the simulations match the real surveys is yet another affirmation that our invisible ingredients are real. By surveying the cosmos on giant scales, we confirm that the large-scale structure requires those shadowy elements. It's as though by cataloguing where galaxies are, we indirectly sketch the invisible gravitating framework underneath them. With each survey, our image of the dark universe comes into sharper focus. Scientists also listen to the darkness using other, more exotic messengers beyond ordinary light. The cosmic microwave background is one such messenger. The faint afterglow of the Big Bang, now cooled and stretched to microwave wavelengths after nearly 14 billion years. Imprinted on this all-sky glow are tiny variations in temperature that reflect the distribution of matter, dark and normal, in the very early universe. By measuring these tiny fluctuations with great precision, missions like COBE, WMAP, and Planck have allowed us to deduce the composition of the universe. The pattern of fluctuations, their sizes and distribution, is like a fingerprint of the cosmos's contents and shape. Analyzing this faint background whisper, scientists found that the data strongly point to a universe dominated by dark matter and dark energy, beautifully consistent with what other methods have found. Even subtle effects, like how the cosmic background's light is slightly altered after passing through billions of light years of expanding space, potentially influenced by dark energy, give us clues. The integrated Sachs-Wolf effect, for instance, is a tiny imprint on the microwave background caused by light crossing through large voids and clusters during a period of accelerating expansion. Detecting such minuscule signals has been challenging, but claims of their measurement offer yet more evidence that dark energy is at work, even in the way seemingly empty space affects ancient light. In these delicate ways, the universe's oldest light and the great cosmic voids themselves speak to us about the shadowy influences pervading space. Beyond light and electromagnetic signals, astronomers have extended their senses with other cosmic messengers. Neutrinos, nearly massless particles born in the hearts of stars and during cataclysmic cosmic events, stream invisibly through space and through us. Enormous underground detectors, often deep in old mines or under mountains, have been built to catch the rare interactions of these ghostly particles. Each neutrino captured is like a whisper from a distant supernova or the sun's core, carrying information that light alone might not convey. While neutrinos primarily open a window on energetic processes in stars and explosions, their successful detection proves we can observe the universe in novel ways beyond traditional starlight. Meanwhile, gravitational wave observatories have begun to feel the faint tremors of spacetime caused by distant cataclysms like merging black holes or neutron stars. These waves are ripples traveling through the fabric of space itself, and in 2015, humanity detected them directly for the first time. By hearing these cosmic vibrations with facilities like LIGO, we added a completely new sense to our cosmic toolkit. Though these methods, neutrinos and gravitational waves, are focused on extreme astrophysical events rather than dark matter or dark energy, they underscore how inventive science has become in listening to the universe's faintest whispers. Each new channel of information, be it neutrino particles or gravity waves, adds to our overall understanding and demonstrates that even in darkness, there is much to detect if we have the right instruments. Back on Earth, researchers also seek more direct evidence of dark matter's nature in deep underground laboratories, often set up in old mines or mountain tunnels, where hundreds of meters of rock shield them from interfering cosmic rays. Gigantic detectors filled with ultra-pure liquids or chilled crystals lie in wait. They are listening in their own way, waiting for the faintest bump in the night. If a dark matter particle drifting through space were to strike an atomic nucleus inside one of these detectors, it could produce a tiny flash of light or a subtle vibration in the crystal lattice that sensitive instruments would record. It's a bit like trying to catch a ghost by the lightest tap it might make on a door. So far, these experiments have not conclusively detected a dark matter particle. No definite whisper from the dark has yet been heard. But with each passing year, they become more sensitive. They push ever closer to the theoretical limits, narrowing down what dark matter can or cannot be. Each quiet night that passes in these subterranean halls without an obvious signal still tells us something, helping refine our picture of this elusive matter. And the quest continues, with scientists around the world upgrading detectors and exploring new techniques in hopes that one day a dark matter particle will indeed announce itself with that faint, long-awaited signal. Meanwhile, powerful particle accelerators, like the Large Hadron Collider, have been marshaled to search for dark matter in another way, by trying to create it. In high-energy collisions, protons are smashed together at nearly light speed, momentarily recreating conditions akin to the very early universe. If dark matter consists of a new kind of fundamental particle, these collisions might occasionally produce them. Such particles would slip through a detector without a trace, invisible, but their presence could be inferred. After a collision, physicists tally up the energies and momenta of all visible particles flying out. If something is missing, as if some energy vanished into the darkness, that could be a sign that an unseen particle carried it away. It's like hearing a tone with a missing note. The gap suggests something we didn't directly hear. So far, no clear dark matter particles have shown up in the LHC or other collider experiments, but the data have helped rule out or constrain many ideas. Like all our other methods, it ultimately comes down to observing what we can see and deducing what we cannot. We notice when something expected is missing, and from that absence, we infer the presence of the invisible. The continuing efforts at colliders keep pushing the boundary, ready to capture any hint of new particles that might emerge. Bit by bit, these many approaches, gravitational lensing, galaxy surveys, cosmic background measurements, underground detectors, high-energy colliders, and more, are painting a fuller picture of the darkness between the stars. We have moved from ignorance to at least a shadowy awareness. We now know that something is out there in the darkness, even if we do not yet know exactly what it is. We have mapped its broad outlines and begun to fathom its influence. The cosmic web has been charted. The great voids have been surveyed. The accelerating expansion has been measured. It is as though we are explorers, mapping a dark continent by the faint lights along its shores and by echoes from unseen mountains in the fog. Each new observation lifts another corner of the veil, and the quest continues. Even now, new observatories and instruments are being prepared to probe the darkness more deeply than ever. Future space telescopes will map billions of galaxies to trace the influence of dark matter and measure the subtle bending of light across the sky. Huge detectors on Earth and in space will push to catch the faintest interactions of dark matter particles, or to refine measurements of the universe's expansion. With each technological advance, we bring the invisible into slightly clearer focus, step by careful step. Yet, despite all we have learned, profound mysteries remain. Dark matter has eluded identification. Its true nature is still unknown. Not one of our sensitive earthbound detectors has yet caught a definitive signal from a dark matter particle. All our evidence for it comes only from the gravity it exerts on the cosmos. Dark energy remains an enigma as well, its essence and origin deeply puzzling. We find ourselves in a universe where we understand the choreography of cosmic evolution, but not the full cast of characters. We can predict the cosmic future under dark energy's sway, but we struggle to comprehend the force itself. In the darkness between, so much is known, and yet so much remains veiled. As we end this part of our journey, drifting in the quiet intergalactic dark, listening to the silent music of gravity and light, we are filled with awe at the unseen majority of our universe. The darkness is not just an absence, but a presence, dynamic, powerful, and brimming with wonders we are only beginning to fathom. Our exploration of these hidden realms has illuminated many secrets, but it has also opened up new questions. What lies beyond the edge of the known universe? Do the answers to dark matter and dark energy await in new physics, or perhaps in phenomena yet to be discovered? The cosmos stretches out far beyond the stars we can see, and even beyond the dark structures we have mapped. It beckons us onward. Gently, the curtain of night draws our curiosity further, inviting us to step beyond the horizon of our current knowledge. Our journey is not over. In fact, it feels as if we stand on a threshold, where the darkness between what we know and what we have yet to discover stretches boundlessly ahead, silent and mysterious, waiting for us to continue the adventure. As we gaze beyond the furthest reaches of our observable cosmos, a profound question arises in our minds. We have traveled in thought to the very edge of what we can see, the cosmic horizon, where galaxies gradually vanish into darkness. Yet even at that horizon, our curiosity does not end. It wanders further, into realms we cannot directly observe. What lies beyond the edge of space as we know it? Could it be that our universe is not the only one, but just one island in a boundless cosmic sea? Some scientists imagine that beyond our cosmic horizon, new worlds are waiting. In this vision, our universe is a single bubble afloat in an endless cosmic ocean. Space itself could be like a frothing sea, with countless bubbles, countless universes, forming and drifting in its expanse. Each bubble universe would have its own space and time, its own galaxies and stars. They might even have different laws of physics, sealed off from one another like ships passing in the night. Picture an infinite emptiness that is not truly empty. Deep in this expanse, energy simmers quietly, much like water about to boil. Given time, that energy might froth and churn, spawning bubbles of new space. Each bubble begins tiny, then expands rapidly, growing into a full-fledged universe. Our own cosmos, with all its billions of galaxies, could have begun as one of these minuscule bubbles. If this is true, then the event we call the Big Bang might not have been unique. Instead of one singular beginning for everything, there could be innumerable Big Bangs, each lighting up its own corner of a greater reality. Somewhere far beyond our reach, another bubble might be expanding right now. It could be an entirely separate universe, sprouting into existence, unknown and unseen by us. These bubble universes would be completely isolated. The gaps between them might be expanding faster than light, preventing any contact forever. We would never know the other universes directly, and they would never know us. Our entire sky, everything we see, is confined to the inside of our own bubble. Yet beyond that boundary, the idea of a frothy multiverse invites us to dream. It tells us that perhaps reality is far more vast and varied than we ever imagined, with other cosmic islands floating out there in the dark. Thinking of the universe this way can be both humbling and exciting. We often feel small when we consider the scale of our universe alone. But if our universe is just one bubble among countless others, then even the grandest expanse we know might be a tiny part of an even greater whole. Like a single point of light in a sea of endless night, our universe could be one among many, an island in an infinite archipelago of universes. How could these other universes come into existence? To explore that, we turn to the strange and subtle rules of the quantum world. On the tiniest scales, what we think of as empty space is not truly empty. It teems with fleeting energy and virtual particles that flit in and out of existence in a haze of uncertainty. These are called quantum fluctuations, random, momentary changes in energy that constantly ripple through the fabric of reality. Some scientists speculate that under the right conditions, a quantum fluctuation could do something extraordinary. It could trigger the birth of an entire new universe. Imagine a tiny region of space where a sudden surge of energy wells up by chance. In our universe, such events happen all the time at microscopic scales, but normally they cancel out and fade almost instantly. Yet if one of these fluctuations were powerful enough, it might inflate into a bubble of spacetime instead of dissipating. This little bubble could then detach from our cosmic environment and expand, growing into a separate universe all its own. In effect, the fabric of spacetime might split off a new bubble, like a budding flower giving rise to a fresh cosmos beyond our own. In such a scenario, each new universe might have different properties. The laws of physics that we take as constants could be more like cosmic tuning dials that vary from one universe to the next. One universe might have stronger gravity or entirely different fundamental particles. Another might be born with an extra dose of dark energy, causing it to expand faster, or perhaps with none at all. The possibilities could be endless. Our universe has the particular blend of forces and particles that allow galaxies, stars, and life as we know it. But out there in other realms, reality might follow a different script. Some universes could be sterile, with no galaxies or light. Others might be exotic in ways we can hardly imagine, each a unique experiment in existence. Parallel realms don't only emerge from cosmic bubbles, they also arise in thought experiments about quantum choice. One famous idea, the many worlds interpretation, suggests that our universe is constantly branching into countless versions of itself. According to this idea, Whenever a quantum event has multiple possible outcomes, all outcomes actually happen, each in its own branch of reality. In one parallel world, a coin toss lands heads. In another, it lands tails. In one, a particular star is born with a certain mass. In another universe, that same star might form slightly differently. These parallel universes would exist in tandem, each unaware of the others, like shadows cast in different directions. If the many worlds picture is true, there could be a staggering number of parallel realities. Every moment of chance or choice would spin off new universes. There might be universes where history took a different turn, where galaxies arranged in alternate patterns, or where life evolved along unfamiliar paths. However, these many worlds are not places we could travel to, nor are they separated by distance. They are like different layers of reality, coexisting but inaccessible to one another. It is a deeply intriguing notion that the universe we experience is just one slice of a far greater multiverse of possibilities, whether through quantum fluctuations, giving birth to new cosmic bubbles, or through the branching of many worlds. The idea of parallel realms stretches our understanding of reality. It forces us to accept that what we see is not all that is, and that creation might be an ongoing process, happening in ways we cannot directly observe. Each parallel universe, born from the quantum foam or split from a decision, would be a self-contained world with its own story. And while we cannot step into these other worlds, the mere possibility of their existence expands our minds and fills us with wonder at the strangeness and breadth of the cosmos. Some theorists even speculate about cosmic gateways between universes. For instance, a black hole in our universe could conceivably pinch off and form a new, hidden universe on the other side of its gravity. In this whimsical scenario, every black hole might be like a seed, planting a new universe beyond our view, connected only by the threads of gravity. It's a speculative idea, not proven by any means, but it shows how far imagination will roam when we contemplate parallel realities. In all its forms, the multiverse concept invites us to think beyond the confines of a single cosmos and consider a panorama of worlds upon worlds. One of the most compelling multiverse ideas arises from the very physics that shaped our own cosmos. Cosmologists believe that in the first fleeting fraction of a second after the Big Bang, our universe underwent an almost unimaginable expansion. This is the theory of cosmic inflation. Space itself swelled exponentially, smoothing and stretching the young universe. Inflation helps explain why the cosmos looks mostly uniform in all directions and resolves certain cosmic puzzles. But inflation might be more than just a chapter in our universe's history. It could be an ongoing process that extends far beyond our observable horizon. The idea of eternal inflation suggests that inflation never completely stopped. While it ended in our region, allowing galaxies and stars to form, in other regions it continued and may still be continuing even now. Space, according to this theory, is like an ever-expanding foam. Most of the foam cools and condenses into bubbles, which become universes like ours. But some parts keep inflating, stretching faster and faster. Those inflating regions, in turn, sprout new bubbles here and there, each bubble becoming a separate universe. In this way, the cosmos becomes a perpetually growing fractal of inflation and bubble universes. There is always more inflating space beyond, spawning new universes without end. Picture a pot of boiling water, where bubbles form, grow, and rise endlessly. Eternal inflation is akin to a never-ending boil, but on a cosmic scale. Even if nearly all of space cools into stable universes, some small patch remains in the furious grip of inflation. That patch expands so rapidly that it quickly outweighs the rest. Within that still inflating space, more bubbles will eventually nucleate, each one a big bang, each one a new universe. Our own cosmos could be one such bubble that stopped inflating long ago, surrounded by an ocean of space still foaming with creation. This process can produce an endless number of universes over time. Inflation doesn't end everywhere at once. It ends in scattered patches. Each patch that stops inflating becomes a bubble universe like ours. But the regions where inflation goes on will keep stretching and generating new bubbles eternally. The result is a cosmos that is constantly giving birth to new universes. There wasn't just one creation event, but a continuous, everlasting genesis unfolding on the grandest scale. Even as we ponder these ideas, far beyond our sight, space could be exponentially ballooning and budding off new universes. What's truly intriguing is that each of these bubble universes might be entirely different in its makeup. When inflation ends in a region, the energy driving that expansion is released and transforms into the matter, radiation, and space-time of a new universe. How this energy converts can vary from one bubble to another. Think of how water freezing can form different patterns of ice crystals. Similarly, as a bubble universe freezes out of the inflationary state, it may settle into a universe with its own distinct laws of physics. The strengths of forces, the types of particles, even the number of spatial dimensions could turn out differently in another bubble. Our bubble cooled into a cosmos that allowed stars and life, but another might cool into a universe that expands too quickly for galaxies to form, or one where atoms, as we know them, cannot exist. Eternal inflation thus implies a vast multiverse, where every bubble universe is another roll of the cosmic dice, each one a unique realization of what reality might be. The scale of this multiverse is almost beyond comprehension. In eternal inflation, the majority of existence would be that raging, expanding space far outside what we can see. Our entire observable universe, enormous as it is, might be just a tiny froth on the edge of an infinite, inflating ocean. It is a humbling perspective. We look out and see billions of galaxies. Yet in the grand scheme of eternal inflation, those might be just one calm bubble amid an ever-growing storm of creation. This fractured cosmos, if it exists, is both beautiful and disorienting. A never-ending tapestry of universes, each isolated in its own bubble, yet all part of an endless cosmic expansion. The concept of a self-replicating cosmos changes how we think about our place in reality. It suggests that our universe, vast as it is, might be just one of countless others, produced by the same cosmic process. In this view, the story of creation is not a one-time event, but an ongoing unfolding across an infinite expanse. This idea, born from inflation theory, takes the multiverse from pure speculation to a natural extension of our best cosmological model. Of course, these other universes are beyond our direct sight, at least for now. Yet the theory of eternal inflation offers a thrilling answer to what lies beyond our cosmic horizon. An endless frontier of new universes, popping into being like cosmic fireworks in the distant darkness. It is a grand vision of creation without end, where our universe is but one spark in an infinite fireworks display. And it invites us to imagine infinity in a new way, not as a quiet void, but as an ever-unfolding landscape of worlds beyond count, beyond the concept of multiple universes separated by vast distance or inflating space. there is another exotic possibility, that other universes might be hidden right next to us in dimensions we cannot perceive. Our everyday experience has 3 dimensions of space: length, width, height, and one of time. Everything we see and feel exists within those dimensions. But some theories, particularly from string theory, suggest there could be additional spatial dimensions curled up or otherwise hidden from us. If these extra dimensions exist, our universe may be confined to just one of them, like a flat surface within a much larger realm. Imagine that all of our known reality is like a membrane, often called a brain, floating in a higher dimensional space, which physicists call the bulk. This idea paints a picture of our universe as a kind of cosmic sheet. There could be other such sheets, other brains, parallel to ours in that higher dimensional space. Each of those brains could be its own universe, complete with stars, planets, and perhaps life, following its own version of physics. They would be separated from us not by unimaginable distance in our space, but by a tiny step in a hidden dimension. One physicist described it vividly. Our universe might be one slice of bread in a big cosmic loaf, with other slices, other universes, stacked beside ours in a direction beyond the dimensions we know. It's a strange concept to wrap our minds around. We could be living right alongside entire other universes and never realize it, because we're like insects, moving on the surface of a pond, unaware of the world above the water. All the matter and light we're made of might be stuck to our own brain, unable to leak off it to reach other brains. This would explain why we don't see these other universes. We literally can't interact with them any more than a 2-dimensional being on a sheet of paper could perceive the next sheet over. In our day-to-day life, those dimensions beyond remain hidden, so the other brain worlds are effectively invisible and unreachable. However, just because we're mostly isolated from other brain universes doesn't mean they could never affect us. Some theories suggest that gravity, unlike light or atoms, might be able to spread out into the extra dimensions. If so, we might feel a faint tug or see an unexplained influence from a neighboring universe through gravity. And in even bolder scenarios, 2 brain universes might occasionally collide or interact. Such an event would be cataclysmic. It could release as much energy as a Big Bang. In fact, one proposal is that our own Big Bang might have been caused by 2 brains smashing together in the distant past, flooding our brain with energy and creating everything we see today. The idea that our universe could have a twin or a multitude of siblings just out of reach in higher dimensions is both mind-bending and wondrous. It suggests a reality where space is much richer than we thought. Not just an expanding bubble, but a layered structure, with each layer a universe. If this picture is true, then beyond the edge of our space might lie another entire cosmos, offset from us in a way we can't visualize, but no less real. It's as if our universe is one chapter in a thick book of cosmoses, and we are only aware of our own chapter. The other chapters, the other universes, could be right there, separated by the thinnest of boundaries, yet they would remain forever out of reach. Still, by contemplating higher dimensions and brain worlds, we expand our understanding of what beyond the horizon might mean. In doing so, we open the door to realities once thought impossible. We have followed the thread of our universe's story back to its earliest moments. But a tantalizing mystery remains. What came before the Big Bang? Conventional wisdom says nothing did. That the Big Bang was the beginning of time itself, the ultimate starting point. In this view, asking what happened before the dawn of time is as futile as asking what lies north of the North Pole. Yet human curiosity is not so easily quieted. Scientists and philosophers alike have dared to imagine that perhaps the Big Bang was not the absolute beginning, but rather a bridge from a prior reality, or the opening chapter of a much larger cosmic cycle. One idea that reaches beyond the Big Bang is the cyclic universe. In this scenario, the universe goes through endless rounds of birth, death, and rebirth. Our cosmos expands from a hot, dense state, the Big Bang, grows for billions of years, and perhaps someday in the far future, it could stop expanding and recollapse under gravity. After shrinking down, it might crunch into an incredibly dense point, only to rebound in a new Big Bang, starting the cycle anew. In this vision, time itself is circular, with no true beginning or final end. In an oscillating universe like this, the Big Bang we know would have been the rebirth following a previous universe's collapse. Time, instead of a line with a start and finish, becomes a loop, with each loop containing a Big Bang, an expansion, and ultimately a contraction back to a big crunch. This concept is ancient in spirit. Echoes of it appear in Hindu cosmology and other philosophies. But modern physics has explored it too, wondering if the laws of nature might allow such eternal cycles. Another perspective comes from the idea we encountered earlier, the brain world scenario. If our universe is a membrane floating in higher dimensions, it's conceivable that the Big Bang was not the beginning of all existence, but simply a violent event within a larger multiverse. Imagine two giant brains drifting in the bulk of higher dimensional space. If they collided, the impact would be enormous. It could heat up matter and energy to fantastic temperatures, effectively causing a Big Bang on each brain. Our universe's birth could have been one of those collisions, a cosmic collision event, rather than creation out of nothing. In this view, there might indeed have been a before, a time when our brain existed in a calm, cold state until another universe brain slammed into it. After the collision, the brains would recoil and our universe would cool and evolve. But eventually, they might drift together again. Each time the brains collide, it would set off another round of cosmic creation. This cyclic brain collision model means our Big Bang was just one of many, strung together by the periodic dance of universes touching across dimensions. There are also radical ideas that don't involve traditional cycles or colliding brains, but instead propose a kind of succession of universes over unimaginable timescales. One notable concept suggests that the remote future of our universe might actually become the seed of a new universe. As the universe expands and ages, it will grow cold and empty as stars burn out and black holes evaporate. At that stage, nothing but thin, diffuse energy would remain. Some physicists propose that when the universe becomes so diluted that it effectively forgets its scale, with no masses or clocks to measure time, the geometry of space and time could reinvent itself. In this view, the death of one universe, an almost featureless expanse, might metamorphose into a new Big Bang, birthing a new universe. It's a mind-bending idea. The end of time in one epoch could act like the Big Bang of the next. In this way, universes could be serial, each one giving rise to the next in an endless lineage. Thus, the cosmos could renew itself indefinitely, with no final end. If any of these notions holds truth, then the Big Bang is not the ultimate boundary we once thought it was. Instead of a firm wall at time's beginning, there could be a doorway, opening into a previous universe, or into a grander network of universes. The other side of the Big Bang might be just as rich with existence as the side we know. Perhaps there was a cosmos before our cosmos, leaving subtle imprints on our world. Or perhaps our universe is one bounce in an eternal cosmic trampoline, forever oscillating. These ideas remain speculative, and they push our understanding of physics to its limits. but pondering them transforms the way we see the cosmos, not as a singular event from nothing, but as an ongoing story, possibly with chapters before our own. In that story, our universe's birth is not a lone miracle, but part of a greater tapestry, one that might extend infinitely backward as well as infinitely outward. Such contemplations remind us that every ending may be a new beginning in disguise. If the Big Bang was a beginning, maybe it was also the ending of something else. We find ourselves confronting the profound possibility that beyond the edge of our universe's origin lies another realm or era, fundamentally connected to ours, yet unreachable by any telescope. It's a mystery at the boundary of science and philosophy, and while we may never be able to truly peek behind the curtain of the Big Bang, the very idea that something could lie beyond it adds another layer of wonder to an already astonishing universe. Our cosmic horizon, it seems, may not just exist in space, but in time as well. And beyond that horizon, who knows what marvels await? Our journey into the possibility of other universes would not be complete without asking, is there any evidence? If these parallel worlds or cosmic bubbles exist, could we ever detect them from within our own universe? It's a daunting challenge. By definition, other universes lie outside our observable realm. We can't simply point a telescope and see into a different universe. However, some scientists have proposed that if another universe once interacted with ours, it might have left behind a faint fingerprint. The idea is that while our universe expanded, if it ever collided or brushed against another universe in the distant past, the aftermath of that encounter could still be observable today in subtle ways. One place to search for such signs is the cosmic microwave background, the dim afterglow of the Big Bang. Cosmologists have scrutinized that ancient light for unusual patterns that might hint at something beyond our universe. Years ago, they discovered an intriguing anomaly, a very large cold spot, a region of the sky cooler than expected. This cold spot was a puzzling blemish on the microwave background. Initially, some thought it might be caused by a gigantic supervoid, an enormous empty region with far fewer galaxies, which could make the light from that direction slightly cooler. But when astronomers looked more carefully, they found no void large enough to explain it. The cold spot remained mysterious. With conventional explanations faltering, attention turned to more exotic possibilities. One daring hypothesis was that the cold spot might be a bruise from another universe colliding with ours long ago. If our cosmic bubble had bumped into another bubble universe, the collision could have disrupted the temperature of the microwave background, leaving behind an unusually cold patch. In fact, some researchers pointed out that standard inflation theory predicts countless other universes. To them, the cold spot could be the first hint of a multiverse. As one astronomer poetically remarked, our universe might be just one island in a vast cosmic archipelago, and the cold spot might be the mark of a neighbouring island's influence on our shores. This idea is still speculative, and scientists are careful to consider other explanations. There's a chance the cold spot could simply be a statistical fluke, a random ripple in the early universe that we're now scrutinizing, with perhaps too much imagination. Some have also explored whether subtle irregularities in the distribution of matter or new physics could cause such a feature. So far, no definitive proof has emerged that the cold spot, or any other anomaly, is evidence of another universe. Still, the mere prospect has spurred new research. Teams have simulated bubble collisions to see what kind of imprint they would leave, and they've combed through high-precision maps of the microwave sky for additional hints, perhaps circular patterns or slight distortions that a clash of cosmic universes might produce. Beyond the cold spot, other potential clues have come under debate. astronomers observed a curious motion in galaxy clusters, with hundreds of clusters seemingly drifting in the same direction, pulled, it appears, by something outside the observable universe. This was dubbed dark flow. Some suggested that a huge structure beyond our horizon was tugging on these clusters through gravity. The dark flow evidence has been controversial, and many scientists doubt it's real. Perhaps future observations will make it disappear, but such investigations show how far we will go to explore even the faintest hints of worlds beyond. After years of searching, no conclusive signal of a multiverse has been found. The cosmic microwave background, with all its tiny ripples and spots, largely matches what we'd expect from a single, self-contained universe. Yet the door is not closed. Future missions will take even more detailed measurements of that primordial light, looking for patterns we might have missed. And scientists will keep refining their models, asking if there's any clever experiment that could reveal the presence of other universes. It may turn out that the multiverse leaves no traces we can detect, remaining an intriguing idea rather than a proven reality. But even so, the pursuit of that evidence has expanded our imagination and sharpened our scientific tools. Standing at the cosmic horizon, we find ourselves at the limit of what we can see, but not at the limit of what we can imagine. The search for other universes, these possible islands in the cosmic sea, is a testament to human curiosity. Each anomaly we investigate, each hypothesis we test, pushes us a little further into the unknown. Whether or not we ever find proof of worlds beyond our own, the very act of searching deepens our understanding of the universe we inhabit. It reminds us that every discovery opens a door to new questions, and that the cosmic horizon is not a boundary so much as a beckoning frontier. As we conclude this leg of our journey, the multiverse remains a grand, unresolved question. We have peered as far as we can into space and time, and imagined beyond that, into an ocean of possible universes. The evidence so far is suggestive, but inconclusive, and yet the idea alone has enriched our perspective. Our universe feels more precious, and at the same time less lonely, when we consider that it might sit among countless others. In the end, whether our universe is one of many, or alone in the vast darkness, our desire to know what lies beyond endures. We continue onward, eyes up to the sky, minds open to infinity, ready to explore whatever may come next, just over the cosmic horizon. We find ourselves standing at the very edge of knowledge, peering into a darkness where certainty fades into mystery. After journeying across vast cosmic landscapes, exploring galaxies, and peering back to nearly the dawn of time, we now face a horizon we cannot cross. It is not marked by a wall or a sign, but by the limits of what the universe will allow us to see and know. Like ancient mariners staring at an endless ocean, we look out at a boundary beyond which our instruments fall silent, and we wonder what lies beyond. This boundary is the cosmic horizon, the farthest reach of our observable universe. For nearly 14 billion years, light has travelled across the expanding space, bringing us images of distant stars and galaxies. But beyond a certain point, even light has not had enough time to reach us. That point is our horizon, a gentle but unyielding limit to our vision. We gaze outward and realize that the universe has been revealing itself to us gradually, but only up to a point. Beyond that, there may be more universe, perhaps endless galaxies stretching far past where we can see, but their light has not yet arrived, and perhaps never will. The reason is woven into the fabric of space-time itself. As we look deeper into space, we are also looking back in time, toward the universe's distant past. When we peer to the edge of what's visible, we see a faint afterglow. the cosmic microwave background, the oldest light in the cosmos. This light has travelled since the universe was young, carrying whispers of how everything began. It forms a kind of luminous veil that marks the limit of our sight. Beyond it, the universe was once too hot and dense for light to travel freely. We cannot see beyond that glowing curtain. It is as far back as electromagnetic signals can take us. Even as the universe expands and time flows on, some horizons remain fixed. Distant galaxies rush away from us, carried by the swelling of space. Many slip beyond a reach from which their light can ever return. Space itself expands so swiftly that it outpaces the speed of light. Galaxies that were once visible become redder and fainter until they vanish from view, like ships disappearing over a distant ocean horizon. They have not ceased to exist, but their light will no longer reach us. In this way, the cosmos imposes a natural limit on how much of itself we can ever explore. We push against these limits with our curiosity and ingenuity. Each new generation of telescopes expands our vision a little further, revealing surprises at the brink of the known universe. Not long ago, we could only see galaxies a few billion light-years away. Now we glimpse galaxies whose light started its journey over 10 billion years ago. With new technology, we strive to approach that horizon, to capture the first faint galaxies that formed, the moment when the first stars ignited. Yet no matter how powerful our tools become, there will always remain a frontier beyond which we cannot see, a frontier set by the universe's own laws. This realization can be humbling. In ages past, when humans mapped the Earth, they imagined edges, literal ends of the world where one might fall off into an abyss. When those edges were finally reached, they discovered new lands and oceans beyond. In space, whenever we think we near an edge, we find more space stretching out, more mysteries unfolding. But now, at the scale of the entire universe, we encounter an edge that might truly be uncrossable. It is not an edge like a cliff or a wall, but a horizon in time and space beyond which information may never reach us. What might lie beyond this ultimate horizon? Perhaps simply more of the same, more galaxies, more clusters of stars and worlds extending far beyond our view. Or perhaps beyond our observable patch, the cosmos takes a different form entirely, with regions governed by different laws or punctuated by strange phenomena we can scarcely imagine. We do not know, and that not knowing is itself a profound part of our experience. At the edge of knowledge, we must accept mystery. We are like explorers on a vast sea. Our charts end here, and beyond them we can only speculate. There are other boundaries to our knowledge too, even closer than the cosmic horizon. Think of the center of a black hole, shrouded by an event horizon, beyond which no information returns, or the very beginning of time, a moment so remote and extreme that our theories falter. In the earliest fraction of a second after the Big Bang, the universe was so hot and dense that our physics breaks down, a veil drawn over what came before. We have models and ideas, but no clear view. At both the smallest scales and the largest expanses, our understanding has edges, like pieces of a grand puzzle with missing parts. And yet, standing here at this cosmic shore, we don't turn back. Instead, we feel a sense of awe at the vastness that remains beyond our grasp. The edge of knowledge is not a line that halts our journey. It's a horizon that calls to us, urging us onward, even if we cannot cross it. There is a gentle wonder in knowing there are things we may never know. It reminds us that the universe is not ours to fully possess. It has depths that transcend our comprehension, perhaps always will. So, we stand in the starlight and breathe in the silence of that unknown. Our minds stretch out as far as they can go, to the point where questions outnumber answers. We reflect on how extraordinary it is that we have come this far, from wondering what lay beyond the next hill, to pondering what lies beyond galaxies. Each generation has extended the borders of the known. Now we reach the border drawn by the universe itself. It is here that our scientific maps end, with a simple notation at the edge. Beyond here, there be mystery. Yet even as we accept this boundary, our curiosity flickers with possibilities. Is the universe infinite beyond our sight? Does it go on forever? Galaxies upon galaxies, without end? Or does it curve back on itself in some exotic way, or transition into realms utterly alien to anything we know? These questions tug at us gently. They lead us to the next step of our journey, a step not into deeper darkness, but into a contemplation of the infinite and the unknowable that beckons from just beyond our horizon. And so, we turn our thoughts to infinity. When we stand beneath a clear night sky, the stars seem to go on forever. It feels as though we are looking into an endless expanse, with no wall or boundary in sight. This sensation, that there might be no end to what is out there, stirs a mix of wonder and vertigo deep in the human mind. Is the cosmos truly infinite, stretching out forever beyond every horizon? Or is there some edge far beyond our reach? This question is as old as our curiosity and as profound as any we can ask. The nature of infinity is elusive. In our daily lives, everything we encounter has limits. The length of a road, the span of a life, the shoreline of an ocean. The concept of endlessness lives mostly in our imagination and our mathematics. We can say the numbers go on forever, but we never experience an actual infinity. And yet, when we consider the universe, infinity appears inescapable. If space goes on without end, then even though we cannot traverse it fully, it exists as a grand reality beyond any physical journey. Imagine traveling through space, passing galaxy after galaxy, for billions upon billions of years. No matter how far you went, you would never come to a final border or a sign that says, the end. If the universe is truly infinite, then beyond each distance you cross lies something more. Even if you could somehow reach the farthest galaxy visible today, beyond it you would find further realms unfolding, new vistas without limit. The idea is both beautiful and disorienting, a reality that has no endpoint. Our minds struggle with such immensity. To help grasp it, we often use metaphors. One analogy is the Earth itself. If you travel in one direction on the Earth, you never fall off an edge. Eventually, you come back around. The Earth's surface is finite, but has no sharp boundary. It curves back on itself. Some have wondered if our universe might be like that on a far grander scale, finite yet unbounded, curving through higher dimensions in a way we can hardly visualize. But it might also be that space is not curved enough to loop around. It could simply stretch out infinitely, an open expanse with no return. If the universe truly extends forever, it carries strange implications. In an infinite expanse, every possible arrangement of matter could exist somewhere. Far beyond our observable patch of galaxies, there could be regions where the cosmos looks very different, where galaxies form different patterns, or maybe where physics itself takes odd turns. And among the limitless possibilities, there could even be another region so uncannily similar to our own that it contains a galaxy like the Milky Way, a star like our Sun, and a planet very much like Earth, with beings wondering about the cosmos just as we do. It's a mind-bending thought. In an infinite universe, the unlikely becomes inevitable somewhere, repeated endlessly in the vastness. But is the universe infinite, or just very vast? Science has not yet given a definitive answer. We measure what we can see, and that is immense, but finite. The observable universe has a size, a horizon, and beyond that, we can only infer possibilities. The universe might wrap around on itself, or it might expand without bound. Both scenarios challenge our understanding. If it is finite, what lies beyond its boundaries? If it is infinite, how do we make sense of a space with no limits at all? The concept of infinity also emerges when we contemplate time. We find ourselves in the flow of time, moving from past to future, and we wonder, did time have a beginning, and will it have an end? If time stretches infinitely into the future, it means forever, truly never ends. The universe could continue in some form, eternally. If time extends infinitely into the past, it would mean there was no first moment, that existence always was. Both prospects boggle the mind. Infinity in time is as staggering as infinity in space, raising the question of whether something can really persist without any boundary or origin. Over centuries, philosophers and scientists have wrestled with the infinite. Ancient thinkers in Greece and India pondered whether the cosmos was boundless or cyclical. Medieval scholars tried to imagine an endless universe created by an infinite divine. In the scientific revolution, as we learned that Earth was not the center of all, the possibility of an infinite universe opened up, startling the imagination of early astronomers. The more we learned, the larger the universe became, and the more the idea of infinity pressed upon our thoughts. In mathematics, we learned to work with infinity as a concept, to handle the infinite with equations and logic. Yet, even mathematicians acknowledge that actual infinity defies full comprehension. There are even different sizes of infinity that mathematics can define, abstract ideas that seem to outstrip any physical reality. But these are symbols and definitions. What does an endless reality mean in concrete terms? It can send the mind spinning in circles. Sometimes, infinity is easier to approach through simple images. Consider standing between two mirrors facing each other. You see an endless corridor of reflections, curving away into the distance. Or think of the horizon at sea on a calm day. No matter how far you sail, the line of the horizon always stays ahead, always out of reach. These analogies are imperfect, but they hint at the feeling of something without end. Infinity is not really a number or a place. It's an idea, one that challenges our intuition at every step. When we try to imagine infinity, we often end up confronting our own limits. Our lives are finite, our experience is bounded. We can imagine adding one more step, one more number, one more year, but doing that forever escapes true understanding. Perhaps our minds are not built to fully grasp infinity. Perhaps it's a concept we can approach only indirectly. And yet, we keep trying. The endless draws us in. The limitless excites our curiosity and ignites our sense of wonder. As we ponder the infinite, we start to sense that it might be more than a mere abstraction. The universe might be infinite in extent or in possibilities, or perhaps reality includes not just this universe, but a multitude of others, a multiverse of infinite variety, where every outcome plays out somewhere across an endless canvas of existence. This is speculative, a wild extension of the idea of infinity. Whether or not such ideas are true, they remind us that infinity, if it exists, could take forms we have yet to even dream of. Ultimately, infinity is a question that leads us beyond the edge of what we can empirically verify. It forces us into the realm of thought experiments and philosophical reflection. Standing here, dwarfed by a possibly boundless cosmos, we feel both small and strangely connected to something vast. We sense that even if we can't fully fathom the infinite, just reaching toward it expands our perspective. It humbles us, showing how much greater reality might be than our corner of it. In the quiet of a starry night, when one contemplates infinity, there's a paradoxical feeling of peace. The endless ocean of stars above does not frighten so much as invite contemplation. We may never travel to the ends of the universe, if an end even exists, but our minds can roam into the boundless, at least in imagination. There is a gentle freedom in that, a sense that beyond all boundaries lies an open question mark, waiting for us to wonder about it. And so, infinity, whether real or not, becomes a part of our story, a backdrop to all our questions. It whispers that beyond every horizon our eyes can see, there may always be more. This realization leads us to wonder. If the universe might be endless, what then is the nature of the reality we perceive? Could our own perception be limited or even deceived? Our journey now turns inward, toward the question of what is real and what might be an illusion. Our perceptions tell us that the world is solid and real, but philosophers have long wondered if that is truly the case. From ancient times to the present, people have asked, could this reality be a kind of illusion? In Plato's famous allegory, humans are like prisoners in a cave, mistaking shadows on the wall for real objects. Only by turning around and seeing the light can they grasp the true forms casting those shadows. In a similar way, perhaps what we see and touch are mere shadows of a deeper reality we cannot directly perceive. Every day, our senses present us with a picture of the world, and we trust it implicitly. Yet those senses can be fooled. We see the sun arc across the sky, and it feels as if we are standing still. Yet we know the earth is spinning. A stick, half immersed in water, looks bent, though we know it is straight. Our eyes and ears are limited in what they detect. We see only a narrow band of light, hear only a range of sounds. Much of reality slips past our notice, and what we do perceive, our brain assembles into an image of the world. In truth, the colours, sounds, and even solidity we experience are all interpretations by our mind. They feel real to us, and they are real experiences, but they are our brain's rendering of external stimuli. We live inside a kind of biological virtual reality, crafted by evolution to make sense of the world. This understanding invites a profound question. If our experience of reality is a construct of the mind, how can we be sure of what lies beyond our perceptions? Philosophers like Descartes once imagined an evil demon that could trick a person's senses entirely, making a false world seem completely real. In modern terms, we might ask, are we living in a sophisticated illusion? Could our entire universe be akin to a dream or a simulation being run on some cosmic computer? It sounds like science fiction, yet serious thinkers have proposed that future technology could create simulations so convincing that the inhabitants would never know. If such simulations are possible, some argue it's plausible that we ourselves might be inside one. The simulation hypothesis suggests that what we consider physical reality might be generated by information processing at a deeper level. Every atom, every star, you and I, would be part of the program's code. From our perspective inside the simulation, everything seems consistent and obeys certain rules, the laws of physics. But if we could step outside, we might see an entirely different picture of reality running on some platform we cannot comprehend. It's a dizzying idea that the ultimate hardware of existence could be something beyond anything we know. And all we experience is a kind of virtual environment. Even without invoking computers and simulations, physics itself offers hints that reality might be not quite what it appears. Consider solid matter. It feels firm, and yet we know at the atomic level it is mostly empty space with tiny particles moving at high speeds. Fields and forces that we cannot see hold everything together. On the quantum scale, particles can exist in uncertain states, seeming to be here and there until observed. Some interpretations of quantum physics suggest that observation, the act of measurement, plays a role in determining what is real. In that sense, the line between the observer and the observed can blur, as if the universe only settles into a definite state when it interacts with a consciousness. Then there is the idea that our universe might be a kind of hologram. This concept doesn't mean the world is literally a laser projection, but that all the information that makes up our 3D space might be encoded on a distant 2D surface. Much like a hologram on a sheet of film can produce a three-dimensional image, the fabric of our cosmos could be the projection of something fundamental at its boundaries. If true, our perception of having depth and volume is real to us, yet fundamentally, it could be akin to a complex illusion generated by underlying data. The holographic principle, as physicists call it, emerged from studies of black holes and quantum gravity. It hints that reality might have layers we are only beginning to uncover. Long before science, mystics and spiritual traditions have spoken of the world as illusion. In Hindu philosophy, the term Maya is used to describe the illusory nature of appearances. The idea that the universe we experience is like a veil, and a deeper spiritual reality lies beyond it. Similarly, some Buddhist teachings compare life to a dream. These perspectives encourage seekers to look past the surface of things, to question the reality presented to them, and to awaken to a truer understanding. They suggest that what we usually call reality might be more like a cosmic stage set or a dream in the mind of the universe. Such ideas do not necessarily deny the existence of the physical world, but they imply that our usual way of seeing it is incomplete. They urge us to consider that there may be more to reality than meets the eye. Perhaps the physical universe is real in its own way, but it is only one layer of a deeper existence. Much as the ocean's surface is real, but conceals the vast depths below. What we take for solid, absolute reality could be just the surface appearance of something more profound. If the universe is an illusion or a simulation, what does that mean for us? For one, it instills a sense of humility. We realize that the truth of existence might be far beyond our immediate grasp. It also raises an intriguing possibility. If there is a creator of the illusion, be it a deity, a cosmic consciousness, or programmers of a simulation, then perhaps what lies beyond this apparent reality is an even greater, richer realm. Yet even within the illusion, our experiences and feelings are genuine to us. A simulated love is still love. A dream of beauty can still stir the soul. The realization that reality might be illusory does not necessarily make life less meaningful. It can make it feel like part of a larger mystery. Moreover, thinking of reality as a kind of illusion naturally leads us to ponder the role of consciousness. After all, an illusion must appear to someone. A dream must have a dreamer. We find ourselves asking, who or what is observing this grand show? Are our minds separate entities, simply experiencing a pre-written script? Or are we participants in shaping reality as we perceive it? This line of inquiry guides us deeper, from the external world of matter to the inner world of awareness. Perhaps, in the end, the key to what lies beyond the apparent cosmos lies within the very phenomenon of consciousness, which we explore next. Consciousness, the simple awareness of being, is one of the most profound mysteries in the universe. Out of all the swirling stars and silent galaxies, here on at least one tiny planet, the cosmos has awakened to itself through living minds. We who gaze at the universe are made of the universe. The atoms in our bodies were forged in ancient stars, and now those atoms have come together to think and feel. In us, and perhaps in other beings on other worlds, the universe is not just unfolding blindly. It is observing, it is wondering, it is dreaming. It's often said that we are made of star stuff, and indeed we are. But even more astonishing is that this star stuff has become self-aware. Consider what that means. The universe gave rise to life, and life developed minds that can hold the universe within them, in thought and imagination. When you look up at the Milky Way on a clear night, you are the cosmos looking back at itself. The eyes with which we behold the galaxy were forged from the materials of that galaxy. In a very real sense, the observer and the observed are one. This realization brings a gentle, wondrous feeling, as if we are participants in a cosmic self-reflection. Yet, for all our scientific advances, consciousness remains deeply mysterious. We can study the brain and map its neurons firing. We can identify which patterns of activity correspond to certain thoughts or sensations. But no scan or measurement reveals why it feels like something to be alive. The redness of a rose, the taste of rain, the feeling of love or sorrow. These subjective experiences, known as qualia, elude physical explanation. How does the grey matter inside our skull produce the bright cinema of our inner life? This is often called the hard problem of consciousness, and it suggests there may be more to the mind than just the sum of physical parts. Perhaps consciousness is not an accidental byproduct of matter, but an intrinsic aspect of reality. Some thinkers have proposed that consciousness might be a fundamental feature of the universe, just like space, time, or energy. According to this view, often referred to as panpsychism, even elementary particles might possess the tiniest glimmer of experience. An electron might not think, of course, but it could have an exceedingly simple form of awareness. If this is true, then as matter becomes more complex and organized, as in a brain, those basic awarenesses combine or magnify into the rich consciousness that we experience. In this way, consciousness wouldn't emerge from nothing at a high level. Instead, it would have always been present in some form, gradually blossoming as the cosmos grows in complexity. Whether or not one accepts that idea, it's undeniable that the potential for consciousness was built into the universe from the start. The Big Bang produced hydrogen and helium, which formed stars, which forged heavier elements, which became new stars and planets. And on at least one planet, those elements assembled into living beings that could feel and think. It's as if the universe knew that one day it would open its eyes. The late astronomer Carl Sagan put it poetically, "We are a way for the cosmos to know itself." In every one of us lies a spark of cosmic awareness, and if the universe is truly vast or infinite, there could be countless other conscious sparks scattered among distant stars. Perhaps different, perhaps profoundly unlike us, but aware in their own ways. The cosmos could be teeming with pockets of awareness, each gazing out at the grandeur around it. Could the universe itself, in some grand and subtle way, be conscious? This idea ventures far into speculation, but it has a long history. Philosophers and mystics have imagined that all individual minds are fragments of one universal mind. Just as a wave is a part of the ocean, our consciousness might be a part of a greater sea of consciousness. When we feel a sense of unity or oneness, in moments of meditation or awe, perhaps we are briefly glimpsing that connection. It might be that the cosmos isn't just a cold collection of matter and energy, but something alive in its own right, with each living being contributing to its self-awareness. Scientists typically approach such claims with skepticism, because consciousness, as we understand it, requires complex networks like brains. The universe as a whole doesn't have a single centralized brain. Unless one considers all the interconnected galaxies and life within them as components of a vast, distributed mind. Interestingly, when we map the large-scale structure of the universe, the cosmic web of galaxies and dark matter resembles, in form, the network of neurons in a brain. It could be coincidence, or it could hint at a recurring pattern in nature. Perhaps organization into networks is a universal principle, and the cosmos organizes itself in a way that, at least metaphorically, mirrors a giant mind. Whether or not the universe literally thinks, the parallel is a reminder that patterns repeat from micro to macro scales. Beyond scientific theories, many spiritual traditions have long regarded consciousness as fundamental. Some speak of a universal consciousness or divine mind underlying all reality. In these perspectives, our individual awareness is like a droplet from the fountain of a great cosmic consciousness. When enlightened sages claim to feel at one with everything, they describe an experience of merging their individual mind with that larger whole. They report that the sense of a separate self can dissolve, revealing an awareness as vast as the sky. It's as though, for a moment, the cosmos becomes aware of itself through a human mind unclouded by ego. Even within our ordinary experience, consciousness defines reality for us. Without conscious beings to observe it, the universe would be silent and dark. No beauty, no awe, no curiosity. It's through our eyes that the stars become majestic, through our emotions that the universe feels wondrous. In that sense, consciousness is not just in the universe. It brings the universe to life, at least from our perspective. The famous question is often posed: if a tree falls in a forest with no one to hear it, does it make a sound? One might extend that to, if no being were ever aware of the universe, would the universe matter, or even meaningfully exist? Perhaps consciousness and cosmos are two sides of one coin, each giving meaning to the other. Still, we struggle to understand what consciousness truly is. Is it a process, a state, a fundamental field? We don't have the answers yet. It remains the most immediate reality for each of us, our own mind, and yet the most elusive to scientifically explain. This humbling ignorance keeps us open-minded. We acknowledge that some aspects of existence might forever lie beyond the complete grasp of equations and experiments. The mind contemplating the cosmos is confronted by the cosmos contemplating itself. What we do know is that consciousness allows us to love, to wonder, to create meaning. It turns the raw data of the world into stories and reflections. Through consciousness, the universe has poetry and music. It laughs and cries. These human things might seem small against the backdrop of galaxies, but they are the way in which the cosmos has become intimate and personal. And so we return to the grand cosmic narrative. We have pondered the possibility that our minds are integral to what the universe is. We have entertained the notion that perhaps the cosmos itself has an inner life. or at least that it is enriched immeasurably by the presence of conscious beings. From here, our thoughts turn to the sweep of cosmic time. Consciousness makes us aware not only of the present, but of the past and future too. We yearn to understand where we came from and where we are headed. In this quest, modern physics presents a startling idea that the fate of the universe might be connected to its origin, that in some way the end folds back to the beginning. It's to this idea that time itself could be a loop that we now turn. For as long as we've studied the cosmos, we've told its story as a line, a beginning, a middle, and an end. Time seems to flow like an arrow. We imagine the Big Bang at one end of time's arrow, shooting forward through the formation of galaxies and stars to where we stand now and onward into the future. But what if that arrow of time eventually curves back on itself? What if the cosmic story is less like a line and more like a circle, with the end connecting back to the beginning? Modern physics, in some of its more imaginative theories, is exploring just that possibility. Our current understanding of the universe's fate goes something like this. The universe began in a hot, dense state and has been expanding ever since. In recent decades, we discovered that this expansion is speeding up, driven by a mysterious force we call dark energy. If this continues, the cosmos will keep dilating faster and faster. Galaxies will drift apart, stars will burn out, and eventually, trillions of years from now, all will grow dark and cold. Matter itself might decay, leaving a thin haze of particles in an ever-growing emptiness. This is the scenario known as the heat death, or big freeze, an end state of eternal cold and darkness, time stretching on, but with virtually nothing happening. It's a bleak, one-way journey into stillness. Yet, not so long ago, many scientists believed a different end awaited the universe. They thought gravity might one day halt the expansion and reverse it. In that scenario, after billions of years of expansion, the cosmos would begin to contract. Galaxies would draw closer, merging. The temperature of space would rise as everything crowded together again. Eventually, all matter and energy would crash together in a spectacular collapse, the Big Crunch. Time would, in a sense, run backward toward an omega point of high heat and density, perhaps not unlike the state in which the universe began. Some speculated that at the moment of that final collapse, a rebound could occur, a new Big Bang igniting from the ashes of the old. In this view, the universe could be cyclic: Big Bang, expansion, contraction, Big Crunch, and then bang again, like an infinite series of breaths in and out, or a phoenix endlessly reborn from its own ashes. Today, the discovery of accelerating expansion has made the Big Crunch seem unlikely for our universe. But the idea of a cosmic rebirth has not vanished. It has evolved. If a traditional collapse won't happen, could there be another way for an ending to lead to a beginning? One imaginative proposal comes from the realm of quantum cosmology: the Big Bounce. In Big Bounce models, the Big Bang was not the absolute beginning, but rather the aftermath of a previous universe that had collapsed. In these theories, when everything squeezes down to extremely high densities, quantum effects, the strange rules that govern subatomic particles, create a powerful repulsive force that prevents a total singularity. Instead of vanishing to an infinite point, the old universe bounces and begins expanding again, this time as our universe. In essence, the end of a previous cosmos becomes the birth of the next, and this cycle could have happened not just once, but over and over. Another radical idea comes from the mind of a famous physicist who suggested a universe that doesn't need a big crunch to start anew. In his scenario, called conformal cyclic cosmology, even an ever-expanding universe can seed the next cosmic creation. It works like this. Imagine the universe in an incomprehensibly far future, so far that black holes have evaporated and all matter is dispersed as low-energy radiation. In that almost empty, uniform expanse, the concepts of distance and time lose their meaning. Without matter, there are no clocks or rulers. At that point, the vast, cold universe of the end starts to resemble the tiny, hot universe of the beginning, at least mathematically. It's as if the dying embers of one cosmos can be reinterpreted as the blazing spark of a new one, through a kind of geometric stretching, a conformal transformation. The infinite end loops around to become a new Big Bang. In this vision, the universe goes through eons or aeons, each with a Big Bang, expansion, and eventual dissipation, followed by the next Big Bang. These cyclical ideas are speculative and not universally accepted, but they captivate the imagination. They also echo very old intuitions. Many ancient cultures believed time was cyclic. Hindu cosmology, for example, speaks of the universe going through infinite cycles of creation, destruction, and rebirth over trillions of years. Long before modern science, they imagined a cosmic rhythm. The ancient symbol of the Ouroboros, a serpent eating its own tail, represents the idea of a cycle that renews itself, an eternal return. It's intriguing that today's cosmologists, armed with equations and observations, are revisiting a notion that time might, in some sense, circle back. What evidence might we find for such cosmic cycles? Some scientists have searched the cosmic microwave background, the afterglow of the Big Bang, for anomalies, patterns that might hint at events that happened before our Big Bang. There have been claims of unusual circular patterns in that glow, perhaps the fingerprints of a previous universe's black hole collisions. These claims are controversial and far from confirmed. If our universe is one of many cycles, proving it may be exceedingly difficult. The connection from one eon to another might wipe away or blur most traces. Still, the very attempt to find out is a testament to human curiosity, reaching for the ultimate horizon of time. Apart from grand cycles of the whole universe, some have even pondered smaller cosmic loops. For instance, could black holes be gateways to new beginnings? When a massive star collapses, it forms a black hole, an abyss from which nothing returns. Some theoreticians muse that perhaps that trapped matter doesn't get destroyed, but instead erupts as a big bang in a baby universe, a whole new expanding reality sequestered away from ours. If so, then every black hole could be a cosmic seed, an end that becomes a beginning elsewhere. Our own Big Bang might even have been born from such an event in another parent universe. These ideas blur the line between an end and a birth on the grandest scales. The loop of time also invites philosophical reflection. If the universe truly cycles, does that mean everything will repeat? Perhaps not exactly. The laws of physics might allow each cycle to differ, but it raises the question of eternal return. Some have imagined that given infinite time, all events might recur in some form. It's a haunting thought. Are we destined to live our lives again and again in future universes? Or is each cycle a fresh canvas, with new possibilities never exactly repeating? At our current level of understanding, we can only speculate. The notion of time as a loop challenges our conventional thinking, where every story has a unique beginning and end. Whether or not our universe is cyclic, considering it opens our minds to the larger context of existence. If there was something before the Big Bang, if the cosmos had a yesterday in some form, then our universe is part of a greater continuum. Likewise, if our universe has an afterlife in a new cosmos, then the story of existence is bigger than the story of this one universe. It suggests that creation and destruction might be two sides of the same coin, a process built into reality. Even in a one-time universe, there's a connection between the start and end. The conditions of the beginning, how much matter, how space is curved, etc., determine whether it will expand forever or recollapse. The fate is written in the initial conditions. In that sense, the end has always been hidden in the beginning. We are like characters in a book, slowly flipping pages toward a known finale, perhaps unaware that the first page already hinted at the last. As we contemplate these grand loops, we realize that the beginning and the end might not be as absolute as we once thought. They could be chapters in a larger cycle. The universe might not have a single story, but an anthology of stories, each giving rise to the next. And even if our universe's tale is one of a kind, we are still left with profound questions. What set it all in motion? What, if anything, lies outside this cycle or beyond time itself? Just as we reach the speculative limit of cosmology, we find ourselves facing questions that border on the philosophical or even spiritual. It is here, at the threshold of knowledge and imagination, that we prepare to step beyond the cosmic horizon one final time, into the realm of pure wonder, where every answer gives birth to new questions. We have travelled a long way, from the familiar shores of knowledge to the farthest reaches of speculation. Now we drift in a sea of mystery, at the edge of space and time, gazing out into a beyond that no telescope can reach, and no equation can fully describe. Here, at the cosmic horizon and beyond, we confront the unknown, not with fear, but with a quiet awe. The vast darkness beyond the stars is not empty for us. It is filled with our questions, our dreams, our wonder. What lies beyond the edge of the universe? It might be other universes, or endless extensions of this one, or realms entirely unlike anything we know. Or perhaps the question itself dissolves at this boundary, and our concepts of beyond and outside simply do not apply. We are like sailors at night on an uncharted ocean, seeing the stars reflected on dark waters, sensing that the ocean goes on far further than our maps. We cannot see the distant shore, there may be none, but we feel the limitless expanse around us. That feeling is both humbling and exhilarating. There comes a point where science meets a veil it cannot yet lift. We have peered back to almost the moment of creation, probed the tiniest particles of matter, and stretched our minds with theories of multiple dimensions and endless time. But after all that, there remains a horizon of ignorance. Beyond it, we have only guesses and imagination, and that is all right. In fact, it is beautiful. The unknown beckons to us like a distant melody, luring us to keep going, keep wondering. The pursuit of knowledge is endless, because each answer uncovers new questions. The cosmic horizon moves as we move, ever out of reach, ensuring that there will always be more to explore. Standing here in thought, at the edge of all that is known, one cannot help but feel a profound humility. The universe is far grander than our minds can grasp. We, who emerged from stardust, have dared to try to understand it, and we have succeeded to an astonishing degree. Yet what we know is a tiny island in a vast ocean of the unknown. The realization could be daunting, but it is also deeply poetic. Our ignorance is not a void to be feared, but a canvas for wonder and creativity. Not knowing everything makes the universe more, not less, majestic. There will always be mysteries to entice us, and perhaps that is a gift. In the darkness beyond the cosmic edge, Some see the face of the divine, others the deep beauty of nature, others the infinity of possibility. Different minds find different meanings in what they cannot see. For some, it is enough to simply feel the immensity and be moved by it. The sense of something transcendent, call it what you will, arises naturally when confronted with an endless unknown. It reminds us that we are part of a reality much larger than ourselves, a reality that perhaps no finite mind can ever fully comprehend. And in that realization, there is a quiet comfort, even a joy. We are participants in a mystery that has been unfolding long before we arrived, and will continue long after we are gone. Think of the generations before us, looking up at the stars with myths and questions. We have answered many of their questions, yet many of our own remain, and in the future, new explorers of thought will stand where we stand, at the new edge of knowledge, looking out and asking, what lies beyond? The torch of curiosity is passed on, and the unknown ensures it will never dim. Every mystery we solve reveals a deeper mystery beyond, in an endless ascent of understanding. We climb a mountain, and at the summit, we discover a higher peak veiled in clouds, waiting to be reached. There is a peaceful acceptance in acknowledging that some things may always elude us. Perhaps our universe is fashioned in such a way that a complete self-understanding is impossible, a cosmic stage where the final act is never played. If so, that does not diminish our quest. It makes it an open-ended adventure. The questions we cannot answer become inspirations, guiding our science, our philosophy, our art. The unknown is the wellspring of our longing to know. At this final juncture, where knowledge blurs into speculation, we find that science and wonder converge. Our tools and measurements have taken us far, and now our imagination takes flight to carry us further. We allow ourselves to dream, to envision possibilities without the need for immediate proof, knowing that one day proof may come, or our dreams may evolve. The line between what is real and what is imagined becomes thin at the edges of the cosmos, and perhaps that is fitting. After all, every accomplishment of science began as a dream, a question whispered into the dark. We return, then, to ourselves, standing under the sky, the same sky our ancestors saw, though we now know it is the window onto a vast universe. We feel the breeze of night and realize it carries the breath of 1 billion stars. Beyond those stars stretch others, and beyond those, perhaps endless more. We know that we cannot walk to the horizon and touch it. It always recedes. The cosmic horizon is like that too. It ensures that the universe always has secrets. And it is those secrets that spice the cosmos with magic, forever preventing it from becoming a mere catalogue of facts. In our journey beyond the edge of space, we have found not a boundary, but a boundlessness. We went seeking what lies beyond the horizon, and we discovered the horizon is not a limit, but an invitation to marvel at things beyond our grasp. Each time we think we've reached the end, a new expanse opens up. There will always be a new question, a new mystery star shining just at the corner of our vision, hinting at wonders yet to come. As we conclude this exploration, we carry with us not a sense of finality, but of continuity. The story of the universe, and our story within it, goes on. We are both tiny and significant. Tiny in the face of the cosmic abyss, yet significant because we bring meaning to it through our curiosity and consciousness. The edge of space is not an end. It is a beginning of imagination. Where our knowledge stops, our sense of wonder begins in earnest. So let us cherish the questions that have no answers. the mysteries that remain. They remind us that we are explorers in an infinite realm, with endless horizon upon horizon. The darkness between the stars is not empty. It is filled with the promise of discovery. The silence beyond the galaxies is not void. It speaks to us in the language of awe. In the end, what lies beyond the edge of space may forever be beyond our complete knowing, but perhaps that is the cosmic horizon, ever out of reach, ensures that we will never cease to learn and marvel. It keeps us looking upward and outward, united by the shared human impulse to seek and to dream. And as we stand here, at the threshold of all we understand and all we don't, we find that the very act of wondering, of embracing the mystery, is its own profound reward. The journey itself is the answer, and the journey never truly ends.